Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. Imagine journeying into the heart of a dying star as it collapses into a black hole. We all know the basics. Nothing, not even light, can escape its grasp. But what if that's not the end of the story? What if this cosmic waterfall has a bottom, and everything that falls in gets blasted out somewhere else in the universe? Are black holes and their theoretical opposites, white holes, secretly connected? And could that connection unlock the secrets of the Big Bang itself? The universe is packed with violent, beautiful, and downright terrifying objects. But nothing has captured our imagination quite like the black hole. It's the ultimate cosmic monster, a spot in space-time where gravity is so intense it devours everything in its path. For decades, we've studied them, feared them, and even managed to photograph their shadow. They represent a final destination, a point of no return. But what if that's only half the story? What if, for every cosmic entrance, there has to be an exit? The known tyrant, deconstructing the black hole. Before we get to the ghost in this story, we need to understand the machine. So, what exactly is a black hole? The name is a little misleading. It's not a hole in space, not some empty void, but the exact opposite. It's an unbelievable amount of stuff crushed into an impossibly small area. To get a handle on this, we have to rewind to Albert Einstein. In his theory of general relativity, Einstein showed us that gravity isn't some invisible rope pulling things together. Instead, it's a curvature of spacetime itself. Picture the universe as a flat trampoline. Now, drop a bowling ball in the middle. The fabric sinks and curves. If you roll a marble nearby, it won't go in a straight line. It'll follow the curve made by the bowling ball. That, right there, is gravity. The Earth is just rolling along the curve made by the Sun. The Moon is rolling along the curve made by the Earth. A black hole is what you get when you push that analogy to its absolute limit. It's not a bowling ball on the trampoline. It's a singularity, a point of nearly infinite mass that has dented spacetime so deeply that the walls of the curve are basically vertical. Once you roll over that edge, no amount of speed can get you back out. The escape velocity, the speed you need to break free, is faster than the speed of light, the ultimate speed limit of the cosmos. And since nothing can go faster than light, nothing can escape. This boundary, the edge of the abyss, is called the event horizon. It isn't a physical surface you'd crash into. It's a purely mathematical line, an invisible front door to oblivion. If you were watching a friend fall toward a black hole, you'd never actually see them cross it. You'd see their image slow down, stretch, and fade away, red shifted into nothing over what seems like an infinite amount of time. To you, they'd be frozen at the edge forever. But for the person falling in, it would feel totally different. No bump, no barrier. They'd just cross the line, probably without even knowing they'd passed the point of no return. Inside the event horizon, space and time themselves get twisted. The direction we call down, toward the black hole's center, isn't a direction in space anymore. It becomes the future. Just like we can't stop moving into tomorrow, an object inside a black hole can't stop moving toward the center. It's not a journey, it's destiny. And at that center lies the heart of the mystery, the singularity. This is where the mass of a dead star is crushed to infinite density. Here, our understanding of the universe, the laws of physics laid out by Einstein, just completely breaks down. General relativity predicts this point of infinity, but it can't describe it. It's a dead end in the math, a place where physics as we know it just stops working. For a long time, this was just accepted as the end. But it's this very breakdown that opens the door to weirder possibilities. It's the crack in the armor of physics where the idea of a white hole starts to creep in. The cosmic horror story, The birth of a black hole. Black holes aren't born quietly. They're forged in the most violent and spectacular events the universe has to offer. The death of a truly massive star. To really appreciate the monster, you have to witness its creation. A cosmic horror story that unfolds over millions of years and ends in a fraction of a second. Picture a star, not like our sun, but a real giant, at least 20 to 25 times more massive. For millions of years, it's a glorious celestial furnace. Deep in its core, a constant battle is raging. The star's own gravity is relentlessly trying to crush it into a single point. Pushing back is the incredible energy from nuclear fusion. The core is a reactor of unimaginable power, fusing hydrogen into helium, helium into carbon, and so on, creating heavier and heavier elements. This outward blast of energy holds gravity at bay in a delicate, fiery stalemate. But this balance can't last. The star is living on borrowed time. As it forges heavier elements, the fusion process gets less and less efficient. Each stage provides less energy to fight back against gravity's constant squeeze. The star's core becomes a layered onion, with lighter elements on the outside and the heaviest, iron, building up at the very center. And iron is the end of the line. Fusing iron doesn't release energy, it consumes it. The star's nuclear furnace sputters and dies. In an instant, the outward pressure that held gravity back for eons vanishes. And gravity, the patient tyrant, finally wins. What happens next is pure chaos. The star's core, with nothing to support it, collapses under its own colossal weight. In less than a second, a region the size of Earth is crushed down to the size of a city. The protons and electrons are squeezed so violently they merge into a sea of neutrons. The density becomes astronomical. This sudden collapse triggers a shockwave that rips back out through the star's outer layers. These layers, which were falling inward, slam into this rebounding shockwave and get blasted into space in a cataclysmic explosion. We see this as a supernova, an event so bright it can outshine its entire galaxy for weeks. The star, in its final moments, seeds the universe with the heavy elements it created, the very stuff that makes up planets and us. But what about the core? What's left after the supernova fades? If the original star was massive enough, the leftover core will still be more than 3 times the mass of our Sun. At that point, known as the Tolman-Oppenheimer-Volkoff limit, nothing in the universe can stop the collapse. The core keeps shrinking, relentlessly. As it shrinks, the gravity at its surface gets insane. Soon, it hits that critical point where its escape velocity becomes faster than the speed of light. This is the moment the event horizon is born. The point of no return. It's like a cosmic waterfall, where spacetime itself is flowing faster than anyone could possibly swim. Go over the edge, and you're swept away forever. From this moment on, the object is a black hole. It has cut itself off from the rest of the universe behind a one-way door. The core continues its collapse, down, 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 until it's crushed into that single, infinitely dense point we call the singularity. The story, for all we knew, was over. A star has died, and a monster has been born. But is that really the end? Inside the abyss, the singularity and the information paradox. So, we've crossed the event horizon. Space and time have swapped roles. The singularity is no longer a place. It's an event in your future you have to experience. But what is it? Like we said, it's a point of infinite density where our best description of gravity, general relativity, just stops making sense. And this isn't a small problem. It's a huge sign that our understanding of the universe is incomplete. Think of it this way. The world of the very large, stars, galaxies, gravity, is described by general relativity. The world of the very small, atoms, particles, is ruled by quantum mechanics. These two pillars of modern physics are incredibly successful on their own, but they absolutely refuse to work together. At the heart of a black hole, these two worlds collide. You have the immense gravity of general relativity acting on an infinitesimally small point, the home turf of quantum mechanics. This clash leads to one of the biggest puzzles in all of physics, the information paradox. A fundamental rule of quantum mechanics is that information can never truly be destroyed. And information here means the unique quantum state of every single particle, its position, velocity, spin. It's an object's fundamental ID. You can burn a book, but its information isn't really gone. It's just been scrambled into the quantum states of the ash, smoke, and heat. In theory, if you could collect every single one of those particles, you could piece the original book back together. But what happens when you throw that book into a black hole? General relativity says it falls past the event horizon and gets erased at the singularity, its information wiped from existence. This is a major violation of the laws of quantum mechanics. So, which theory is right? The great physicist Stephen Hawking made this mystery even deeper. By applying quantum mechanics near the event horizon, he realized that black holes aren't completely black. They should slowly leak radiation back out into space, a process now called Hawking radiation. Over incredible amounts of time, trillions upon trillions of years, this energy leak causes the black hole to slowly evaporate and, eventually, disappear completely. This makes the paradox even worse. If the black hole disappears, what happened to the information of everything it ate? Did it truly vanish forever? Hawking originally thought so, which was a deeply unsettling idea. It meant our understanding of reality had a fundamental flaw. But most physicists, including Hawking later in his life, couldn't accept that. Information must be preserved, so we have a cosmic puzzle. A black hole swallows information. Quantum mechanics says information can't be destroyed. The black hole then evaporates. Where does the information go? This paradox has driven theoretical physics for decades, forcing scientists to hunt for a new theory of quantum gravity that can finally unite Einstein's world with the quantum realm. And it's out of this desperate search that a ghostly, long-forgotten idea from the math of general relativity has made a comeback: the white hole. What if the singularity isn't an end, but a gateway? What if the information isn't destroyed, but just rerouted? The ghost in the machine, introducing the white hole. If information can't be destroyed, it has to go somewhere. If a black hole is the ultimate prison, a place you can only enter, could there be a cosmic portal you can only exit? This is the wild idea of a white hole. In the simplest terms, a white hole is a black hole played in reverse. It's a perfect time reversal of its dark twin. While a black hole's event horizon is a point of no return, a white hole's event horizon is a boundary of no admission. Nothing, not even light, can get into a white hole from the outside. Instead, matter and energy are constantly and violently spewing out from it. It's a cosmic fountain, a source instead of a drain. And this isn't just sci-fi. White holes are a completely valid mathematical solution to the same equations of general relativity that predict black holes. When physicists first solved these equations back in the early 20th century, they found these strange, time-reversed solutions hiding in the math. For a long time, they were just dismissed as a mathematical curiosity, something that couldn't exist in the real world. I mean, how would a white hole even form? We have a clear, observed process for making black holes: a massive star collapses. But playing that movie in reverse makes no physical sense. It'd be like watching an egg unscramble itself, or a supernova explosion running backwards to form a perfect star. That would violate the second law of thermodynamics, which says that disorder in the universe always has to increase. A white hole seems to be a source of pure order, creating things from nothing. Even if a white hole could somehow pop into existence, it would be incredibly unstable. Think about it. A white hole is defined by the fact that nothing can get in. But it still has mass, which means it still has gravity. Any tiny speck of dust or stray photon that fell toward the white hole wouldn't be able to enter. But its energy would pile up at the event horizon, and that pile-up would, according to the theory, almost instantly cause the white hole to collapse on itself and become, you guessed it, a black hole. So, for decades, white holes were tossed on the chalkboard of theoretical weirdness. They were mathematically possible but seemed physically absurd. But the information paradox changed everything. The desperate need to find a way for information to escape a black hole forced physicists to take another look at these forgotten ghosts in the equations. Maybe they weren't a separate, absurd object. Maybe they were the other side of the coin. What if a white hole isn't something that forms on its own, but is what a black hole becomes? The secret connection, wormholes and cosmic rebirth. So, how could a black hole, the universe's ultimate trap, become a white hole, its ultimate fountain? This is where we get to the absolute cutting edge of physics, where things get really weird. There are two main ideas for how these cosmic twins might be secretly connected. The first, and most famous, is the idea of a wormhole, also known as an Einstein-Rosen bridge. This concept also comes straight from the math of general relativity. The theory suggests that a black hole's singularity might not be a point of infinite density, but a throat that connects to another point in spacetime. The black hole is the entrance to a tunnel, and the white hole is the exit. Anything that falls into the black hole is simply transported through the wormhole and shot out of a white hole somewhere else entirely, maybe even in a different universe. It's a beautiful idea that neatly solves the information paradox. Information isn't destroyed, it's just transported. But, like with most things in this field, there's a catch. This classic wormhole is now understood to be hopelessly unstable. The tunnel would pinch off and collapse so fast that not even a single photon could make it through. To keep it open, you'd need some kind of exotic matter with negative energy or negative mass. Something we've never seen and have no reason to think exists. That dead end has led to a second, more modern, and maybe even more profound idea that comes from the search for a theory of quantum gravity. One of the leading contenders is called loop quantum gravity, or LQG. LQG suggests that spacetime isn't a smooth, continuous fabric like Einstein thought. Instead, it proposes that space is made of discrete, indivisible atoms, or loops, of spacetime, the smallest possible units in the universe. You can't have a distance smaller than one of these loops, just like you can't have less than one atom of gold. This completely changes what happens inside a black hole. According to LQG, the collapse of matter can't form a true, infinitely dense singularity. Why? Because you can't crush something into a space smaller than a single atom of spacetime. The matter collapses and gets incredibly dense, but when it hits this fundamental quantum limit, it can't go any further. At that point, the quantum nature of gravity itself creates an immense repulsive force. The collapse halts and literally bounces. This big bounce inside the black hole transforms the collapsing matter into an expanding state. The black hole, from the inside out, essentially turns into a white hole. This gives us a physical way for a black hole to become its time-reversed twin. Information isn't lost at a singularity, it's just compressed to an unimaginable degree and then shot back out during the white hole phase. But if this is happening, why don't we see black holes exploding all around us? The answer is one of general relativity's weirdest effects, gravitational time dilation. To someone falling into the black hole, the collapse and bounce might happen very quickly. But for us watching from the outside, the intense gravity slows down time to an almost complete standstill. The whole process, from formation to slow evaporation to the final bounce into a white hole, would take trillions upon trillions of years from our perspective, far longer than the current age of the universe. This means any white holes we might see today would have to be the end product of primordial black holes, tiny ones that might have formed in the very early universe and are only now, after an eternity, completing their transformation. Some physicists even speculate that some of the mysterious, powerful fast radio bursts we detect could be the signature of these ancient black holes finally turning into white holes and releasing their stored information. The grand implication and the final mystery. This connection between black holes and white holes isn't just a clever fix for a physics puzzle. If it's true, it could fundamentally change how we see the cosmos, our origins, and our ultimate fate. Let's start with the biggest idea of all, the Big Bang. Our standard model describes it as the moment our universe exploded into existence from an incredibly hot, dense state. It was a singular event, an eruption of all matter and energy that expanded into the cosmos we see today. Now, think about our description of a white hole. A singular event where a huge amount of matter and energy erupts from a single point. The descriptions are almost identical. Could it be that our entire universe, our Big Bang, was the result of a white hole? This isn't just a loose comparison. Some models based on loop quantum gravity explore this exact idea. In this Big Bounce cosmology, our universe didn't start from nothing. Instead, there might have been a previous universe that collapsed under its own gravity into one giant black hole. But instead of ending in a final singularity, it reached that maximum quantum density, bounced, and re-emerged as the white hole that gave birth to our universe. In this picture, our universe is the child of a parent universe. Black holes aren't just cosmic dead ends, they're cosmic wombs, gateways to rebirth. Every black hole in our universe could, in the far, far future, become the seed for a new Big Bang and a new universe. It's an eternal cycle of cosmic death and rebirth. This theory might also hold an answer to another of the universe's great mysteries, dark matter. Dark matter is an invisible substance that makes up about 27% of the universe. We know it's there from its gravity, but we have no idea what it is. One speculative but fascinating idea is that dark matter is made of the leftovers of these black hole to white hole transitions. The theory suggests that after the main eruption, a white hole could settle down into a tiny, stable, plank-sized remnant with about the mass of a human hair. While tiny on their own, the countless primordial black holes that may have formed in the early universe could have all turned into these stable white hole remnants, and their combined mass could account for all the dark matter we detect today. Of course, this is all on the very frontier of science. We have no direct proof of white holes or bouncing universes. These are ideas born from trying to solve the deep contradictions in our best theories. But they show us that the universe is far stranger, more mysterious, and more deeply connected than we ever imagined. The black hole might not be an end. The singularity might not be final. They could just be a veil, hiding a connection to a reality far grander than our own. The journey from a collapsing star to a potential new universe is a testament to human curiosity. We started with a simple question: what happens when gravity wins? And it has led us to the edge of reality itself. Black holes may not be a one-way street to oblivion after all, but a revolving door in the cosmic architecture. The information they consume might not be lost, but simply waiting to be reborn. Which leaves us with one final thought to chew on. If our universe did begin with a white hole, what black hole, in what other universe, did it come from? The universe's bedtime story, a black hole's secret twin. As you drift off to sleep, have you ever wondered where the universe's bedtime stories are told? They aren't written in books of paper and ink, but in the silent, velvet fabric of space itself. They're whispered in the pull of gravity and sung in the ancient light of distant stars. Tonight, let's leave the busy world behind and journey together to the very edge of reality, where a story we thought we knew takes a beautiful, unexpected turn. We all know the tale of the black hole, a cosmic monster whose story always seems to end in darkness. But what if that's not the end? What if the darkness is just one side of the page? What if it has a secret twin? A twin born from the same math, but which tells a completely different story. A story not of falling in, but of bursting out. A tale of a white hole. Tonight, we'll gently pull back the curtain of space-time to explore this cosmic secret. We won't rush. We'll travel slowly, peacefully, as if in a dream, and unravel the beautiful mathematics that first whispered this possibility into being. It's a story of symmetry, of secret passages, and the startling idea that the end of one story might just be the beginning of another. So, take a slow, deep breath. Let the quiet of the cosmos settle around you. Our journey to the heart of this mystery begins now. The canvas of the cosmos. Before we can read this secret story, we need to understand the language it's written in. It isn't a language of words, but of curves and dimensions. It's the language of general relativity, a story first told to us by Albert Einstein over a century ago. For most of history, we pictured the universe as a vast, empty stage, a dark box where stars and planets moved, pulled by an invisible force called gravity. We knew it pulled apples from trees and held the moon in orbit, but we saw it as a mysterious command sent instantly across the void. Einstein invited us to see it differently. He asked us to imagine that the stage itself, the very fabric of space and time, wasn't a rigid backdrop. Instead, he pictured it as a dynamic, flexible entity, like a vast, cosmic trampoline. This four-dimensional surface, which he called space-time, is the canvas for the entire history of the universe. And gravity, he realized, isn't a force that travels across this canvas. Gravity is the shape of the canvas. Picture it now. A perfectly flat, infinitely large, dark sheet is stretched out before you. Silent and still. This is a universe with nothing in it. Now, place a heavy ball on the sheet. See how it sinks, creating a gentle dimple. That's what a planet, like our Earth, does to space-time. It creates a shallow curve. If you roll a tiny marble nearby, it no longer travels in a straight line. Its path is bent by that dimple. It curves towards the heavier ball, compelled to follow the geometry of the surface. It's not being pulled by an invisible strain. The shape of the space it's moving through has changed. That's gravity. Now, imagine we place a much heavier ball on the sheet, a bowling ball representing our sun. The curve it creates is deeper and wider. The planets are like marbles rolling around the edge of this deep well, their orbits simply the straightest possible paths they can take through curved space-time. They are in a constant state of free fall, following the contours of the valley created by the sun. This is the heart of Einstein's magnificent idea. Matter tells space-time how to curve, and space-time tells matter how to move. This relationship isn't just a nice analogy, it's the law. Einstein gave us the precise grammar for this cosmic language in his field equations. You tell them how much mass and energy are in a certain place, and they tell you, with perfect accuracy, exactly how space-time will bend and warp in response. For years, physicists explored these new rules, mapping out the strange shapes space-time could take. And in doing so, they stumbled upon a shape so extreme, so bizarre, it would challenge our very understanding of reality. They found the blueprint for a monster. The birth of a black hole. Our journey now takes us to the life and death of a truly enormous star, many times larger than our sun. For millions of years, it's a brilliant furnace, waging a constant, titanic battle with itself. The immense outward pressure from nuclear fusion is perfectly balanced by the relentless inward crush of its own gravity. This delicate balance is what lets a star shine. But this battle can't last forever. Eventually, the star's fuel runs low. The outward push weakens, and gravity begins to win. The star's core, with nothing left to hold it up, starts to collapse under its own colossal weight. For a smaller star, this collapse is stopped when its atoms can't be squeezed any closer. But for a truly massive star, gravity is unforgiving. The collapse doesn't stop. The pressure becomes so intense that atoms are crushed. Protons and electrons are forced together to become neutrons. Still, it continues, unstoppably. This is where Einstein's trampoline becomes essential. As the star's mass is crushed into an ever smaller space, the dent it makes in spacetime gets deeper and steeper. Imagine that bowling ball on our trampoline being replaced by something of the same weight, but the size of a pinhead. The curvature becomes a sharp, deep spike. As the collapse continues, this curvature reaches a critical point. A boundary forms, a line in the cosmic sand. This boundary isn't a physical surface you could touch. It's a geometric threshold where the curvature is so intense that the rules of space and time themselves twist. This is the event horizon. The event horizon is the ultimate point of no return. It's a one-way door in the universe. Anything that crosses it, a stray asteroid, a cloud of gas, even a beam of light, can never come back out. The pull is so strong that the escape velocity exceeds the speed of light. Since nothing can travel faster than light, escape is impossible. From the outside, you would see time for an object falling in slow to a crawl, appearing to freeze at the edge until it fades into nothing. But from the object's own perspective, it passes right through, never knowing it has just left our observable universe forever. Inside the horizon, space and time swap roles. The direction toward the center, which was once a direction in space, becomes the future. Just as we are all pulled towards tomorrow, anything inside the event horizon is now pulled inexorably toward the central point. All paths, all possible futures, lead to one single destination, the singularity. At the very center, classical general relativity tells us there is a point where the star's mass is crushed into zero volume and infinite density. Here, the trampoline of spacetime isn't just curved, it's torn. Our known laws of physics break down. Space and time lose all meaning. The story of the star seems to end in utter oblivion. For decades, this was the accepted story. But the math that described this terrifying object held a secret symmetry, pointing to something far stranger. The secret in the math. Our story now introduces a new character, a German physicist named Karl Schwarzschild. The year is 1915. Einstein has just published his theory of general relativity, and the equations are notoriously difficult. Most physicists thought finding an exact solution for something as simple as a star would take years. But Karl Schwarzschild was a prodigy. While serving on the Russian front during World War I, amidst the chaos of trench warfare, he turned his mind to Einstein's equations. Within weeks, he did what many thought impossible. He found the very first exact solution. He wrote to Einstein from the front lines, and Einstein was astonished, writing back, "I had not expected that one could formulate the exact solution of the problem in such a simple way." Schwarzschild's solution was a perfect mathematical portrait of the gravity around a single, spherical mass. His equations revealed a critical value, a specific radius for any given mass, which we now call the *Schwarzschild radius. He showed that if you could compress an object down within this radius, squashing the Earth to the size of a marble, it would form an event horizon and become a black hole. This was the mathematical birth of the black hole. But here's where the story takes its unexpected turn. Schwarzschild's complete solution was bigger than just the black hole. When physicists explored the full, maximally extended, version of his geometry, they found it didn't just describe a black hole. It described its perfect opposite. Most laws of physics don't have a preferred direction for time. A video of two billiard balls colliding makes sense forwards or backwards. When physicists applied this idea of time reversal to Schwarzschild's solution, something incredible happened. The equation for a black hole, an object that only pulls things in, transformed into an equation for an object that only spits things out. This is the white hole. A white hole is the time-reversed mirror image of a black hole. It's a hypothetical region of spacetime that can't be entered from the outside. Just as nothing can escape a black hole, nothing can get into a white hole. It's a boundary of absolute exclusion. While a black hole is a cosmic trap, a white hole is a cosmic fountain, a violent gusher of matter and energy. Anything on the inside would be forcefully ejected, spewing out into the universe like a spontaneous explosion. Schwarzschild's pure mathematics, derived in the trenches of a world war, had not just predicted the black hole. Baked into its very structure was the blueprint for its secret twin. The math insisted on this symmetry. It showed a black hole region in the future, where things fall in, and a white hole region in the past, from which things burst out. The story of an object collapsing into darkness was mathematically tied to a story of an object exploding into light. And this symmetry suggested something even more profound, a connection. The bridge between worlds. The idea that the math of a black hole also described a white hole was mind-bending enough. But the complete solution held one more fantastic secret. It didn't just describe two separate objects. It described them as being connected by a theoretical tunnel through spacetime. This concept was later explored by Einstein himself and his colleague Nathan Rosen, and it became known as an Einstein-Rosen bridge. Today, we call it a wormhole. Imagine our trampoline of spacetime again. A black hole creates a deep funnel. A white hole is an inverted funnel, a hill pushing things away. The Einstein-Rosen bridge connects the bottom of the black hole's funnel to the top of the white hole's hill. It's like folding spacetime so that two distant points touch, with the wormhole being the narrow passage that connects them. This paints an extraordinary picture. If you fell into a black hole, you might not be crushed at a singularity. You could, in theory, travel through the wormhole and emerge from the white hole, either somewhere else in our universe or in another universe entirely. A black hole isn't a tomb, it's a doorway. It's a beautiful idea, but as physicists looked closer, they found serious problems. The original Einstein-Rosen bridge isn't stable. The tunnel opens and closes so fast that not even light has time to make the journey. It's a bridge that collapses the instant you step on it. Furthermore, a white hole itself is a paradox. For one to exist, it would have had to be there since the Big Bang. Since we don't see any, most physicists concluded that white holes were just a ghost in the equations, a beautiful but physically irrelevant dream. For a long time, the story ended there. But recently, a new chapter has begun, one that brings in the strange and wonderful rules of the quantum world. A quantum bounce. For decades, two things stood in the way of this story. The first was the singularity, that point of infinite density that acted as a full stop. The second was a discovery by Stephen Hawking. He realized that due to quantum effects at the edge of the event horizon, black holes aren't perfectly black. They should give off a faint glow, now called Hawking radiation. Over unimaginable timescales, far longer than the current age of the universe, this radiation causes the black hole to slowly evaporate and disappear. This led to a huge problem, the black hole information paradox. The laws of physics say that information about an object, its unique properties, can never be truly destroyed. But if a black hole swallows information and then evaporates into a featureless glow, where does the information go? It was a deep contradiction. To solve it, we need a theory that can unite gravity with quantum mechanics, a theory of quantum gravity. We don't have a complete one yet, but promising ideas like loop quantum gravity are changing the story. In these new theories, the singularity may not exist. The fabric of spacetime itself might be made of discrete, indivisible atoms. There's a fundamental limit to how small things can get. This simple change has a profound consequence. As a star collapses, it doesn't crush down to an infinite point. It crushes down until it reaches this fundamental, minimum size, where it can get no smaller. At that moment, the quantized nature of spacetime itself creates a powerful outward pressure, a quantum bounce. The implosion is violently reversed. The collapse becomes an explosion. In this new picture, A black hole doesn't end in a singularity, nor does it simply evaporate into nothing. Instead, quantum effects near its core trigger a dramatic transformation. The black hole bounces and transitions into its opposite, a white hole. The information that fell in isn't destroyed. It's compressed to an unimaginable degree and then, through this quantum bounce, spewed back out. The black hole becomes a white hole. The entrance becomes the exit. This neatly solves our paradoxes. There's no impassable singularity, and the information isn't lost. And because of the extreme time-stretching effects of gravity, this process, which might be quick for the matter itself, would take an extraordinarily long time for an outside observer. Billions, even trillions of years. A black hole that formed in the early universe might only now be ready to pop and become a white hole. This has led to some tantalizing, though highly speculative, ideas. Could some unexplained, high-energy bursts we see from deep space be the death cries of ancient black holes finally transitioning? Could the Big Bang itself have been a white hole exploding into being? The other side of a black hole from a parent universe? The hidden twin in Schwarzschild's equations might not have been a ghost after all. It might have been a prophecy of a black hole's ultimate fate. So, as our journey comes to a close, we're left with this wondrous thought. The story of the black hole, which we thought was a tragedy ending in darkness, might actually be a story of cosmic recycling. A story of a long, slow transformation that turns an end into a new beginning. The black hole and the white hole may not just be mathematical curiosities, but two acts in the same grand play, the inhale and the exhale of the universe itself. For now, the white hole remains a beautiful theory, a whisper in the grand symphony of the cosmos. We have never knowingly seen one. Their existence is a dream born from elegant mathematics and quantum possibility. But it's a powerful dream. It suggests that even in the most destructive corners of the universe, there is a hidden symmetry, a potential for rebirth. As you close your eyes and drift into your own dreams, let your mind wander back to that cosmic trampoline. See the deep, dark well of the black hole. But now, see it not as a final destination, but as a passage. A long, quiet tunnel that, after eons, opens up into a brilliant fountain of light. A fountain that seeds the cosmos with new matter, new energy, and perhaps even the spark of new universes. The universe's bedtime story doesn't end in darkness. It hints that for every ending, there is a beginning. For every collapse, a bounce. And for every black hole, somewhere in the deep, unwritten future of spacetime, a secret twin is waiting to be born. If this journey helped you relax and see the universe as a slightly more magical place, I would be so grateful if you would subscribe and join us for more gentle stories from the cosmos. Every tale we tell is another step on our shared journey of wonder. Black holes are not the end, they're the beginning. We've always been told this is the end. A cosmic tomb where everything, even light, is lost forever. We see them in our nightmares and our science fiction, abyssal voids that devour stars, planets, and any hope of escape. For decades, they have been the universe's ultimate symbol of finality. A one-way ticket to oblivion. But what if we've been looking at it all wrong? What if the most destructive force we've ever conceived is also the universe's ultimate creator? What if the place where physics breaks down, where time itself is said to stop, is actually the site of a spectacular rebirth? Imagine that the end of everything is actually the start of something new. Today, we journey to the very edge of scientific understanding, into a radical and breathtaking idea that is gaining ground at the frontiers of physics. An idea where black holes aren't the universe's cemeteries, but its wombs. Portals that don't just swallow worlds, but create them. This is the story of how the universe might recycle itself, and how the end might not be the end at all. The foundation, anatomy of a cosmic monster. Before we can understand how a black hole might be a beginning, we have to understand why we've always seen it as the end. What is this cosmic monster that has captivated and terrified us for over a century? At its heart, a black hole is a surprisingly simple concept. Think of it as a region of spacetime where gravity is so colossally powerful that nothing, not even light, the fastest thing in the universe, can escape its pull. This isn't a place you can visit and leave, it's a destination with no return trip. The story of most black holes begins with a death, the death of a truly gigantic star. Imagine a star many times more massive than our own Sun. For millions of years, it's been a brilliant furnace, fusing elements in its core and pushing outward with unimaginable energy. This outward push from nuclear fusion is in a constant, delicate battle with the inward crush of the star's own immense gravity. But stars, like all things, run out of fuel. When a massive star burns through its nuclear reserves, the outward pressure just stops. Gravity, patient and relentless, finally wins the war. In a fraction of a second, the star's core collapses in on itself with catastrophic violence. The outer layers are blasted away in one of the most spectacular events in the cosmos. A supernova, an explosion so bright it can briefly outshine an entire galaxy. What's left of the core, if it's massive enough, keeps collapsing. Gravity crushes matter to a density our minds can barely wrap around. It compresses and compresses, pulling space and time down with it, until it forms what we call a black hole. So, what are the parts of this strange new object? The most famous feature is the event horizon. This isn't a physical surface you could touch. You wouldn't bump into it. It's an invisible, spherical boundary, the point of no return. Once you cross the event horizon, the gravitational pull is so overwhelming that you'd need to travel faster than light to escape. And since nothing can, your fate is sealed. It's the universe's ultimate one-way door. Surrounding the black hole, you'll often find an accretion disk. This is a swirling, incandescent ring of gas, dust, and stellar debris that's been captured by the black hole's gravity but hasn't crossed the event horizon yet. As this material spirals inward, friction heats it to millions of degrees, causing it to glow so brightly it can be seen from across the universe. This is the paradoxical light that illuminates the edge of darkness, the final scream of matter before it vanishes. And at the very center, according to Albert Einstein's theory of general relativity, lies the singularity. This is the part of the black hole that has vexed physicists for a century. It's a point of theoretically infinite density, where the core of a star may be 30 times the mass of our Sun is crushed into a space with zero volume. At the singularity, our known laws of physics, including Einstein's own equations, break down completely. They give us answers of infinity, which is nature's way of telling us we're missing a piece of the puzzle. For decades, this point of infinite collapse has been seen as the true end, a place where matter, space, and time cease to have meaning. It's the dead end of the cosmos. Or is it? The journey inward, crossing the threshold. To truly grasp the shift in thinking about black holes, we have to follow the path of the unfortunate, the brave, or the just plain curious. Let's imagine we are on a journey, piloting a spacecraft towards a supermassive black hole, like Sagittarius A*, the behemoth at the center of our own Milky Way galaxy. From a great distance, it's invisible, a patch of perfect blackness against the starry canvas. But as we get closer, its presence becomes undeniable. Not by what we see of it, but by how it affects everything around it. Starlight from behind the black hole appears to bend and distort, an effect called gravitational lensing. The very fabric of spacetime is being warped by this immense concentration of mass, like a heavy ball on a rubber sheet. Our instruments detect something profound happening to time itself. According to Einstein's theory of relativity, gravity warps time. The stronger the gravity, the slower time flows. This is known as gravitational time dilation. If we were to watch a clock fall towards the black hole from a safe distance, we would see its ticks get slower and slower. The light from the clock would become redder and dimmer as gravity stretched the light waves and stole their energy. From our perspective, the clock would appear to freeze completely at the edge of the event horizon, stuck in time for all eternity, before fading to black. But for us, as we continue our descent, time feels perfectly normal. Our own clock ticks at 1 second per second. It's the rest of the universe that seems to be speeding up. Looking back, we would see the future of the cosmos playing out in fast forward. Stars would be born and die in the blink of an eye. Galaxies would evolve. Millennia, even billions of years, could pass in the outside universe during our short fall. Now we approach the event horizon. There's no grand explosion, no shimmering barrier. We simply drift across an invisible line. One moment we could, in theory, turn around and escape. The next, we can't. It is a quiet and irreversible transition. Inside the event horizon, the nature of space and time fundamentally shifts. All paths, no matter which direction you try to go, now lead to one place, the center. Trying to escape the singularity is as futile as trying to stop yourself from moving into tomorrow. The future is a single point. For a smaller, stellar mass black hole, our journey would end here in a rather unpleasant way. The gravitational pull on our feet would be so much stronger than the pull on our head that we would be stretched, elongated, and torn apart into a thin stream of atoms. A process with the grimly perfect name of spaghettification. However, we're falling into a supermassive black hole. Here, the event horizon is so far from the center that the difference in gravity across our body is negligible. We could, in theory, cross the event horizon completely intact, floating peacefully in the darkness, unaware for a few moments that our fate has just been sealed. But the journey isn't over. We're now falling through a region of spacetime that is collapsing in on itself. The darkness deepens. All the light from the universe we left behind is now compressed into a tiny, brilliant point behind us. Ahead, there is only the inevitable. We are on a collision course with the greatest mystery in physics, the place where everything we know about the universe comes to an end, the singularity. According to classical physics, this is the final stop. Annihilation, the end of the story. For 100 years, this was the accepted truth. But science, like the universe, is always evolving. And at the heart of this impossible point of infinity, a new idea was waiting to be born. The paradox, where physics breaks. We've arrived at the central mystery, the cosmic paradox that has kept physicists up at night for half a century. We are at the singularity, or at least, where its asterisk supposed to be. According to Einstein's general relativity, this is a point of infinite density and zero volume where the laws of physics simply stop working. But another pillar of modern science, quantum mechanics, which governs the world of the very small, fundamentally disagrees. Quantum mechanics tells us that nothing can be infinitely small or infinitely dense. There are fundamental limits. This clash between our two most successful theories of the universe, the theory of the very large, relativity, and the theory of the very small, quantum mechanics, is the heart of the problem. It's a giant signpost telling us our understanding is incomplete. The singularity probably isn't a real physical object. It's a signal that we need a new theory, a theory of quantum gravity. But the problem gets even deeper. In the 1970s, the brilliant physicist Stephen Hawking realized that when you apply quantum principles near the event horizon, black holes aren't perfectly black. They should glow, ever so faintly, with a thermal energy now known as Hawking radiation. This radiation is caused by quantum fluctuations in the vacuum of space, where pairs of virtual particles and antiparticles constantly pop into and out of existence. If a pair appears right at the event horizon, one particle might fall in while the other escapes. To an outside observer, it looks like the black hole is emitting particles. This process carries away energy, which means the black hole slowly loses mass. Over unimaginably long timescales, it will eventually evaporate completely, disappearing in a final flash of light. And this leads to one of the most profound puzzles in all of science: the black hole information paradox. One of the bedrock laws of quantum mechanics is that information can never truly be destroyed. You can scramble it, but you can't delete it. If you burn a book, in theory, you could piece it back together by gathering every particle of smoke, ash, and heat. The information isn't gone, just rearranged. Hawking's original calculations, however, suggested the radiation from a black hole was purely thermal and random, containing no information about what fell in. This would mean that if you threw a dictionary into a black hole, all the information contained in its words would be utterly erased from the universe. This can't be right. It violates the core rules of quantum physics. For decades, this paradox felt like an impassable wall. But the story has changed. The old picture of a stalemate is gone, replaced by a wave of recent breakthroughs. Physicists now believe the information isn't lost at all. Groundbreaking new ideas, like entanglement islands, suggest that the information is subtly encoded in the outgoing Hawking radiation through quantum connections with the black hole's interior. While the debate isn't fully settled, the consensus is growing. Information does get out. The paradox isn't a dead end anymore. It's a doorway to a deeper understanding of how the universe works. The radical idea, the quantum bounds. That wall between general relativity and quantum mechanics demanded a new kind of physics. For some theorists, the answer lies in a promising, though still developing, field called loop quantum gravity, or LQG. Championed by physicists like Carlo Rovelli and Abhay Ashtekar, LQG proposes a radical new picture of reality. It suggests that spacetime itself isn't a smooth, continuous fabric like Einstein imagined. Instead, if you could zoom in to the smallest possible scale, the Planck scale, you would find that spacetime is made of discrete, indivisible atoms, or loops, of space. It's granular, like a digital image is made of pixels. There is a smallest possible unit of space, a fundamental resolution to the universe. This one idea changes everything. If space can't be divided infinitely, then it can't be compressed to an infinitely small point. The singularity, as a point of zero volume and infinite density, is simply impossible in this view. So, what happens instead? Let's go back to our journey. As the matter of the collapsed star crushes inward, it gets denser and denser. The curvature of spacetime becomes more extreme. But it doesn't go on forever. When the collapsing matter hits the maximum possible density allowed by the fabric of spacetime, it can't be compressed any further. At this point, quantum gravity effects become so powerful they generate a tremendous outward pressure. The collapse halts, and in an instant, it rebounds. This is the quantum bounce. The infalling matter doesn't hit a wall of infinite density. It bounces. This rebound is so powerful that it completely alters the geometry of spacetime inside the black hole. The region that was once collapsing inward transforms into a region that is explosively expanding outward. A black hole becomes a white hole. A white hole is a theoretical object predicted by the same equations of general relativity that predict black holes. It is, quite literally, the time-reversed version of a black hole. While nothing can escape from a black hole's event horizon, nothing can enter a white hole's event horizon. It's a cosmic fountain that violently spews out matter and energy. For a long time, physicists dismissed white holes as a mathematical curiosity that probably couldn't exist. But the quantum bounce provides a physical mechanism for their creation. They could be the next stage in the life of a black hole. This is a monumental shift in perspective. The black hole is no longer a tomb, it's a cocoon. The singularity isn't an endpoint, it's a transition point. A quantum furnace that takes the crushed remains of a dead star and forges them into the seeds of a new creation. The black hole doesn't destroy the universe, it recycles it. The new beginning, a universe recycled. The idea of a black hole turning into a white hole through a quantum bounce isn't just an elegant theory. It has profound implications that could solve some of the deepest mysteries we face. First, it offers a compelling, though still debated, solution to the black hole information paradox. What happens to the information in the dictionary that fell into our black hole? It isn't destroyed at a singularity, because there is no singularity. Instead, the information is compressed and stored during the collapse, held in the unimaginably dense, bouncing state. Then, when the black hole transitions into a white hole, the information is released back out. It's scrambled and transformed, but it's not lost. The universe's fundamental bookkeeping remains intact. The movie of the cosmos can, in principle, be rewound. So, what would this cosmic rebirth actually look like? This is where the strange nature of time and gravity plays a crucial role. For an observer falling into the black hole, the collapse, bounce, and ejection might happen very quickly. But for us watching from the outside, the picture is completely different. Due to extreme gravitational time dilation, the entire process would be stretched over immense cosmological timescales. We would see the black hole form and then slowly evaporate via Hawking radiation over trillions upon trillions of years. The final, explosive eruption of the white hole would appear to us as the very last moment in the black hole's life. A final pop, as the last bit of energy escapes. The black hole lives an incredibly long life from our perspective, but for the matter inside, it's a shortcut to the distant future. This leads to another tantalizing and highly speculative idea. What if the remnants of this process are all around us? Some physicists, including Carlo Rovelli, have proposed that after most of the black hole's mass has evaporated and it transitions, what's left behind is a tiny, stable, Planck-sized remnant, a mini white hole. These objects would be incredibly small and would interact almost exclusively through gravity. They would be, in effect, a form of dark matter. If primordial black holes formed in the early universe and have been undergoing this transition throughout cosmic history, the universe today could be filled with these stable white hole remnants. While this is an untested conjecture, it's an exciting possibility that could connect the largest structures in the cosmos to the smallest scales of quantum gravity. Now, let's take this concept to its ultimate conclusion. If a black hole in our universe can bounce and create a white hole, what about a black hole in a much older parent universe? This brings us to the most breathtaking speculation of all. What if our own Big Bang was the result of a white hole explosion? Could it be that our entire universe is just the recycled material from a star that collapsed into a black hole in another cosmos? In this scenario, the singularity of the Big Bang is replaced by the quantum bounce of a primordial black hole. Our universe didn't emerge from nothing. It erupted from the heart of a black hole, painting an incredible picture of cosmic inheritance. Fecund universes. This grand idea, that black holes are the engines of cosmic creation, was taken a step further by physicist Lee Smolin with a hypothesis he calls cosmological natural selection, or the theory of fecund universes. Smolin proposed that we could apply the principles of Darwinian evolution not just to life, but to entire universes. The idea goes like this. Every time a black hole forms and creates a new, baby, universe via quantum bounce, the fundamental constants of physics in that new universe might be slightly different from the parents. Think of it as a slight, random mutation in the universe's DNA. Now, consider which universes would be most successful in this cosmic ecosystem. A universe whose physical laws are good at making black holes will, by definition, have more offspring. Over countless generations of universes, a process of natural selection would favor those universes whose physical constants are optimized for making lots of black holes. Our universe is incredibly good at it. The laws of physics seem finely tuned to allow for the formation of massive stars that live long enough to seed the cosmos with heavy elements before collapsing. If the constants were just slightly different, stars might not form, or they might not become black holes. Smolin's theory, while highly speculative, offers a potential explanation for the fine-tuning problem, the mystery of why the laws of physics seem so perfect for complex structures like galaxies, stars, and us. The answer, in this view, isn't a lucky accident. It's because we live in a universe that is the product of eons of cosmic evolution, a descendant of a long line of universes that were great at reproducing. We exist not because the universe was made for us, but because the physical laws that allow for our existence also happen to be the ones that are excellent at creating black holes. Our journey has taken us from the familiar image of the black hole as a cosmic predator to the frontier of theoretical physics, where it's reimagined as a cosmic creator. We started with the death of a star, plunged through the point of no return, and faced the paradox where our best theories of reality seemed to fail us. But in that failure, we found a new path forward. A path paved by the granular pixels of spacetime, leading not to an infinite singularity, but to a quantum bounce. A rebound so powerful it could turn a cosmic tomb into a cosmic womb, transforming a black hole into a white hole. This collection of ideas, still taking shape in the minds and mathematics of physicists, has the power to resolve the information paradox, to potentially explain dark matter, and even to give us a radical new origin story for our own Big Bang. It suggests we might live in just one branch of a vast, cosmic family tree, a universe born from the heart of another. We don't know for certain if any of this is the final answer. These ideas exist at the absolute limit of what we can currently test. But they have fundamentally changed the conversation. They have turned the ultimate symbol of an end into a powerful symbol of a beginning. The black hole teaches us a profound lesson: that even in the places of greatest destruction, the universe may hide its greatest creative potential. The end is not the end. It is a transformation. It is a new beginning. The cosmic ghost. The hole that spits out universes. We live in a universe of profound and beautiful violence. Stars are born in fiery nurseries, live for billions of years, and die in cataclysmic explosions that seed the cosmos with the elements of life. But some deaths are stranger than others. Some stars, the true giants, die and leave behind a ghost. An object so dense, so powerful, that it tears a hole in the very fabric of reality. We all know the story of the black hole. It's the universe's ultimate taker, a one-way street to oblivion where gravity is king and nothing, not even light, can escape. We've seen their shadows, we've detected the gravitational waves from their cosmic collisions, and we know they lurk in the centers of galaxies, including our own Milky Way. They're the monsters in the dark, the final word in a star's story. But what if I told you that the very same equations that predict these cosmic monsters, the elegant, revolutionary math of Albert Einstein's general relativity, also predict their perfect opposite? Their bizarro twin, a cosmic ghost that does nothing but give, an object that you can't enter, only exit, a place where matter, light, and energy erupt into existence. This is the story of the universe's ultimate giver, the white hole. In this journey, we'll explore this incredible, mind-bending concept. We'll investigate the theoretical case for its existence and the wild possibility that our own universe was born from one. And then, we'll uncover the fatal flaw, the deep, fundamental problem that makes this cosmic ghost so unstable, it almost certainly can't exist. The investigation begins, defining the ghost. To understand a white hole, you first have to picture its more famous sibling. Imagine a star, many times more massive than our Sun, running out of fuel. For billions of years, the outward pressure of nuclear fusion held the crushing force of its own gravity at bay. Now, that pressure is gone. The star's core collapses catastrophically, squeezing an immense amount of mass into an infinitesimally small point, a singularity. This singularity warps space-time so severely it creates a bottomless gravitational well. Surrounding this well is an invisible boundary, a perimeter of no return known as the event horizon. Once you cross it, all paths, every possible trajectory through space and time, lead only to the center. There is no escape. That's a black hole. Now, take that entire process and run the film backward. That is a white hole. A white hole is, simply put, the time reversal of a black hole. Where a black hole is the ultimate taker, a white hole is the ultimate giver. It's a hypothetical region of spacetime that you can't enter from the outside. Instead of pulling matter and energy in, it furiously spews them out. Imagine trying to approach its event horizon. You'd find that no matter how powerful your rockets, you could never cross it. Spacetime itself would seem to conspire to push you away, with every path leading outward. It's like gravity working in reverse, a fountain of cosmic energy erupting from a single point. The properties we associate with black holes, mass, spin, charge, would theoretically apply to white holes, too. They'd still attract matter just like any other massive object. You could orbit a white hole just like a planet orbits a star. The huge difference lies entirely at that critical boundary, the event horizon. For a black hole, it's a one-way door leading in. For a white hole, it's a one-way door leading out. This isn't just some science fiction idea. The concept emerges directly from the math that underpins modern cosmology. Einstein's equations for general relativity, which describe gravity as the curvature of spacetime, are time-symmetric. This means any solution that describes something moving forward in time also describes a valid process moving backward in time. Think of a video of a ball falling and bouncing. Played forward, it falls. Played backward, it launches itself off the ground. Both are physically plausible, even if one is way more common. When physicists first solved Einstein's equations for a simple, non-rotating mass, they found the solution describing what we now call a black hole. But because of that time symmetry, a second, equally valid solution was right there in the math. It was the negative square root solution, so to speak, a black hole running in reverse. It describes an object that has its singularity not in the future, but in its past. It describes a white hole, destined from its first moment to expel matter and energy. So, what would one of these cosmic ghosts actually look like? From far away, it might be hard to tell apart from a black hole. It would have mass and bend the light of stars behind it. You might even see a glowing disk of gas and dust swirling around its event horizon. The telltale sign, the smoking gun that screams, "white hole," would be the moment it did something a black hole never could: erupt. A sudden, violent burst of matter and energy would spew out from its center. And once it was empty, it would be gone. This vision is beautiful and symmetric. For every taker, a giver; for every entrance, an exit. The math allows it. The logic seems to hold. But our story is just beginning. We've identified our suspect. Now we have to dig deeper into the case for its existence, starting with the moment our own universe was born. The alibi. The mathematical and theoretical case. Every cosmic detective knows that to understand a suspect, you have to understand their origin story. The white hole wasn't just a random idea. It was born from the most successful theory of gravity ever devised, Albert Einstein's general theory of relativity. This theory is the bedrock of modern cosmology, predicting everything from the bending of starlight to gravitational waves, all confirmed with stunning precision. And hidden deep within its math, like a ghost in the machine, lies the white hole. The story starts in 1915 with Einstein's field equations. Just months later, a German physicist named Karl Schwarzschild, serving on the front lines of World War I, found the first exact solution: the spacetime geometry around a single, spherical mass. He had, on paper, described the black hole. But his full solution contained more. It described an object with two event horizons. One was the future horizon of a black hole. The other was a past horizon, a boundary from which things could only emerge. He had also, without naming it, described a white hole. Even stranger, his complete solution connected these two objects through what we now call an Einstein-Rosen bridge, or more famously, a wormhole. According to this pure math, falling into a black hole in one universe could lead you out of a white hole in another. This gave the white hole a solid alibi. It wasn't just a quirky thought experiment. It was a necessary part of the most complete solution to Einstein's equations for a black hole. It had a pedigree. For decades, this was mostly a mathematical curiosity. Most physicists, including Einstein, thought the structure was too weird to exist in the real world. Then, in the late 20th century, quantum mechanics breathed new life into the case. One of the biggest problems in physics is that general relativity predicts an infinitely dense singularity at the center of a black hole, where physics breaks down. Many believe this is where quantum mechanics should take over. This is where a theory called loop quantum gravity, LQG, enters our investigation. LQG suggests that spacetime itself is made of tiny, indivisible, loops. According to this idea, when a collapsing star shrinks toward this fundamental limit, it can't compress any further. Instead, it undergoes a quantum bounce. In this scenario, the collapse halts and rebounds, eventually turning the black hole into its opposite, a white hole. All the matter that fell in over billions of years would be spewed back out in a single, violent eruption. This black hole to white hole transition might even solve the famous information paradox by releasing all the information that ever fell in. This theory, explored by physicists like Carlo Rovelli, suggests a white hole isn't an eternal object but the final stage in a black hole's life. However, due to extreme time dilation, this process would look incredibly slow to us. A black hole forming today might not bounce for trillions upon trillions of years, far longer than the current age of the universe. This provides a perfect alibi for why we haven't seen one. They haven't happened yet. But perhaps the most audacious theory for the white hole places it not in the distant future, but in our most distant past. Some cosmologists have proposed that the Big Bang itself was a white hole. The description fits surprisingly well. The Big Bang was a past event from which all the matter and energy in our universe erupted, and we can't see what came before it. In this picture, our universe could be the result of a black hole from a parent universe that bounced. So, the alibi is strong. White holes appear in the original solutions to Einstein's equations. They're a key prediction of theories like loop quantum gravity. And they offer a potential explanation for the origin of our cosmos. The case seems stronger than ever. But now, we have to turn to the physical evidence, or the lack of it. And this is where the whole case begins to fall apart. The fatal flaw, the case collapses. In any good detective story, there's a moment when the seemingly airtight alibi crumbles. For the white hole, that moment comes when we move it from the perfect world of math into the messy reality of our universe. It's here we find two fatal flaws that make the white hole so fragile, its existence becomes a near impossibility. The first flaw is its profound instability. A white hole's defining feature is an event horizon that nothing can enter. But the universe isn't empty. It's filled with the faint afterglow of the Big Bang, the cosmic microwave background, CMB. Imagine our white hole, sitting in space, constantly being hit by these ancient photons. Theory says it should repel them. But here's the catch. Even a single deflected photon would transfer a tiny amount of energy, creating a ripple in the white hole's perfect geometry. This tiny ripple would start a catastrophic feedback loop. Any matter or energy falling toward the white hole wouldn't be perfectly repelled but would get stuck at the increasingly unstable horizon. The energy would build, its gravity fighting the outward push, until the entire structure collapsed into its much more stable twin, a black hole. This isn't a slow process. The instability is so extreme that the faint whisper of the cosmic background radiation would likely trigger the collapse on incredibly short timescales. It's a soap bubble so delicate that the slightest breeze of reality makes it pop. But even if a white hole could form in total isolation, it faces a second, more fundamental challenge. It seems to violate one of the most sacred laws of physics, the second law of thermodynamics. This law is, simply, the law of increasing disorder, or entropy. It's why eggs don't unscramble themselves and smoke doesn't gather back into a cigarette. It is the arrow of time, pointing from order to chaos. Black holes are entropy champions. They take ordered structures, like stars, and crush them into a state of maximum disorder. A white hole must do the exact opposite. It would have to take a singularity, a state of maximum entropy, and spew out organized matter and energy. This would be like running a woodchipper in reverse and having it spontaneously reassemble splinters back into a piano. It's a massive, spontaneous decrease in entropy, so statistically improbable it's considered impossible. The universe overwhelmingly prefers paths that increase disorder, and a white hole swims directly against that current. This is the 1-2 punch that collapses the case. First, its structure is too unstable to survive contact with our universe. Second, its function seems to defy the fundamental arrow of time. Decades of searching the skies have turned up no smoking gun. There was a flicker of excitement in 2006 with a strange gamma-ray burst, GRBO 60614. It was a long burst of energy that wasn't linked to a supernova, leading some to speculatively propose it as the signature of a white hole. However, this remains an outlier, and most astronomers believe other explanations are far more likely. The cosmic ghost remains a ghost. Its alibi, so strong in the pure world of theory, dissolves under the harsh light of physical reality. The equations might allow it, but the universe seems to forbid it. And yet, the story isn't quite over. Because even if white holes can't exist, the idea of them points us toward some of the deepest mysteries of all. The lingering mysteries. What if? The case seems closed. The evidence is in. The white hole is a beautiful idea undone by the harsh realities of physics. A rational cosmic detective would file the report and move on. But the greatest mysteries are rarely so tidy. Even in their impossibility, white holes leave behind a trail of what ifs that lead us to the very edge of understanding. What if that fatal flaw, the instability, isn't a bug but a feature? This is the core of the black hole bounce idea in loop quantum gravity. In this theory, a black hole does form, but quantum effects stop it from creating a true singularity. Instead, it enters an incredibly dense state that lasts for trillions of years before bouncing and exploding as a short-lived white hole. This isn't the eternal fountain from the old theories. It's a small bang, a single, violent pulse. The instability is exactly what you'd expect from such an event. The reason we don't see them isn't because they're impossible, but because the universe is too young for the first black holes to have reached the end of their lives. They are ghosts of a future yet to come. So where could the evidence be hiding? Some researchers have speculated that mysterious fast radio bursts, FRBs, or other high-energy cosmic rays, could be the death cries of ancient, tiny black holes finally making the transition. We might have been looking at the evidence all along without knowing it. Then there's the grandest, what if, of all. What if we're living inside the evidence? The idea that the Big Bang was a white hole remains one of the most mind-bending concepts in cosmology. Our entire observable universe could be the interior of a white hole, born from a black hole in a parent cosmos, forever cut off from where it came from. This would make our origin not a beginning from nothing, but one link in an eternal chain of cosmic death and rebirth. The idea of white holes even forces us to confront dark matter. In a fascinating recent theory, physicists including Carlo Rovelli have proposed that stable, Planck-sized white holes could be dark matter. If microscopic black holes formed in the early universe and quickly bounced, they could have become tiny white holes that interact only through gravity. They would be dark. They would be everywhere. They would fit the description. This idea is highly speculative, but the search for possible signs is ongoing. These lingering mysteries show why the white hole, even as a failed suspect, is so important. The investigation forces us to confront the biggest questions in physics, pushing us to the intersection of general relativity and quantum mechanics where our theories break down. It makes us question the nature of time itself. The white hole is a paradox. It exists perfectly in Einstein's equations but seems rejected by the physical universe. It's the time-reversed twin of a black hole, yet our universe clearly prefers one over the other, an asymmetry that is itself a profound mystery. So, our detective story comes to a close. We started with the familiar darkness of the black hole and journeyed into the theoretical light of its bizarro twin, the white hole. We followed clues in Einstein's math that said for every taker, there should be a giver. We saw how modern quantum theories gave our ghost a new origin story, recasting it as the explosive finale to a black hole's life. But then, we confronted reality. We found a crippling instability that means a white hole would be torn apart by the faintest whisper of the universe. We learned that its very existence would mean unbreaking an egg, violating the fundamental arrow of time. The cosmic ghost, it seems, is too fragile for our world. And yet, we're left with a sense of wonder. The mystery of the white hole isn't a failure of physics but a signpost pointing toward a deeper reality. It tells us the boundary between black holes and white holes, past and future, destruction and creation, might be blurrier than we ever imagined. The possibility that our own universe was born from one, or that dark matter is made of their microscopic remnants, keeps the case file tantalizingly open. White holes may never be found. They may remain mathematical ghosts, haunting the equations of relativity. But they're a powerful reminder that we live in a universe that's not only stranger than we imagine but stranger than we can imagine. The cosmos is filled with mysteries, and the search for answers, even for ghosts, is what drives us to look up at the night sky in the first place. If this journey into cosmic mysteries sparked your curiosity, be sure to subscribe so you don't miss our next exploration. We have a vast universe of wonders to explore together. And please, share your thoughts in the comments. Do you think white holes are just a mathematical fantasy, or could they be the key to unlocking the universe's greatest secrets? Quantum theory just revealed black holes are new Big Bangs. What if the Big Bang wasn't the beginning? What if the most destructive objects in the cosmos, black holes, aren't endpoints but gateways? Some scientists now suspect that our entire, vast universe might have been born inside a black hole that exists in another, older reality. This isn't just science fiction. It's a scientific hypothesis, born from the strange and wonderful marriage of Einstein's relativity and the quantum world. It's an idea that could rewrite everything we thought we knew about existence and our place in the cosmos. The story of our universe may not have a definite beginning or end, but instead be part of an infinite cycle of cosmic death and rebirth. We're about to journey to the edge of space, time, and understanding itself to unravel a cosmic mystery suggesting that black holes are not graves, but wombs, and our Big Bang was not a singular event, but just one birth among countless others. Prepare yourself, because we are exploring one of the most profound and mind-altering ideas in all of science. The concept is simple, yet its implications are staggering. Every black hole could be the seed of a new universe. Our own Big Bang might have been the explosive result of matter collapsing into a black hole in a parent universe. This theory suggests we are living inside the creation of a black hole, and the hundreds of millions of black holes in our own cosmos might be giving birth to new realities we can never see. This isn't just a wild guess. It's a potential solution to some of the deepest puzzles in physics, an idea that emerges when we try to unite our two best descriptions of reality, the very big and the very small. The cosmic crime scene, a universe too perfect. Before we can understand the solution, we have to appreciate the problem. And the problem is this: our universe is suspiciously perfect. It appears to be exquisitely, unbelievably fine-tuned for existence. Physicists call this the fine-tuning problem, and it's one of the biggest challenges to our understanding of the cosmos. Think of it like a cosmic crime scene. The clues are the fundamental constants of nature, the numbers governing everything from the strength of gravity to the mass of an electron. When we examine these numbers, we find they are balanced on a knife's edge. Let's start with gravity. Cosmologically speaking, gravity is incredibly weak. If it were just a little bit stronger, stars would burn through their fuel millions of times faster, not giving complex life a chance to evolve. If it were slightly weaker, stars and galaxies might never have formed at all. Our existence depends on gravity being exactly as weak as it is. Then there is the strong nuclear force, the glue that holds atoms together. If the strong force were just 2% stronger, all the hydrogen in the early universe would have fused together, leaving none to fuel long-lived stars like our Sun. If it were slightly weaker, protons couldn't stick together at all, and we'd have a universe of only hydrogen, no carbon, no oxygen, no planets, and no people. But the most staggering example is the cosmological constant. This number represents the energy of empty space itself, what we call dark energy, and it's responsible for the accelerating expansion of our universe. When physicists first tried to calculate this value, they got a number that was absurdly large, so enormous it should have ripped the universe apart moments after the Big Bang. Instead, the observed value is about 120 orders of magnitude smaller. That's a 1 followed by 120 zeros. Getting this number by chance would be like throwing a dart from one side of the known universe to the other and hitting a bullseye just 1 millimeter wide. It's the most inaccurate prediction in the history of physics, and it means our universe has a set of rules that seem tailor-made for stars, galaxies, chemistry, and life. This is deeply unsettling for physicists. It feels too coincidental, too much like a setup. Was this universe made for us? Or are there countless other universes with lethal conditions, and we just happen to be in the one that works? This is the central mystery. Is it a fluke? Is it evidence of a creator? Or is there a third option, a natural, scientific explanation for why our universe appears so perfectly suited for existence? To find that, we need to review the standard story of our cosmic origins, and where that story starts to break down. The usual suspects, our standard story of everything. The accepted narrative of our universe is a tale of two theories: the Big Bang, which describes the beginning, and black holes, which classically represent the end. For decades, this has been the standard model of cosmology. Let's start with the Big Bang. Around 13.8 billion years ago, everything in our observable universe was compressed into a point of unimaginable heat and density, the famous singularity. From this point, the universe began rapidly expanding. In the first few minutes, it was a searing hot soup of particles. As it cooled, atoms formed, releasing a flash of light we now observe as the cosmic microwave background, a faint, thermal echo of the Big Bang that fills the entire sky. The evidence, from this background radiation to the expansion of the universe, is overwhelming. But it has a gaping hole. The Big Bang theory brilliantly describes what happened after the beginning, but tells us nothing about the beginning itself. The singularity remains a mystery, a moment where our laws of physics completely break down. What caused it? What came before? The standard model offers no answers. Now for the other half of the story: black holes. Like the Big Bang, A black hole also arises from Einstein's theory of general relativity. When a very massive star collapses, its gravity becomes so intense that it creates a region from which nothing, not even light, can escape. The event horizon. According to general relativity, at the heart of the black hole lies another singularity, a point of infinite density where matter is crushed out of existence. For decades, black holes have been seen as cosmic dead ends. They swallow matter and information, seemingly removing them from the universe forever. This led to the famous information paradox, a deep conflict between general relativity and quantum mechanics, because quantum mechanics insists that information can never truly be destroyed. So this is our standard story. A universe that begins with an inexplicable singularity and ends, for some matter, in another. It's a good story, but it's incomplete. The very existence of these singularities is a giant red flag, a sign that our theories are missing a crucial piece of the puzzle. A crack in the case, the problem with infinity. In physics, when infinity shows up in an equation, it's a warning sign. It signals that your theory has been pushed beyond its limits and has broken. Both the Big Bang and black holes, as described by Einstein's general relativity, led to these singularities, points of infinite density. A singularity isn't a real, physical object. It's a placeholder for a deeper understanding we haven't yet reached. This is where our story takes a sharp turn into the weird world of the very small, quantum mechanics. While general relativity governs planets and stars, quantum mechanics describes the subatomic realm of particles and forces. And it is this theory that comes to the rescue, because in the quantum world, infinity is forbidden. One of its cornerstones is the Heisenberg uncertainty principle. It states you can't know both the exact position and momentum of a particle. This isn't a limitation of our tools, it's a fundamental property of reality. This inherent fuzziness is what prevents the formation of a true, infinitely dense singularity. As matter collapses, quantum mechanics steps in and says, "Not so fast." The more you squeeze a particle into a tiny space, the more it pushes back with a sort of quantum pressure. This quantum pushback prevents matter from ever reaching a state of infinite density. The singularity, as a point of zero volume, simply cannot exist in a quantum universe. Instead of a mathematical breaking point, we get what physicists call a quantum bounce. Matter collapses to an incredibly high, but finite, density and then rebounds. This idea completely changes our picture of both the Big Bang and black holes. The Big Bang might not have started from an infinitely small point, but from the bounce of a previously collapsing universe. And at the center of a black hole, matter isn't destroyed. Instead, it's a place of transition. The collapse is halted, and what was falling in must, somehow, come back out. By applying quantum principles to the extreme gravity of a black hole, physicists opened the door to a revolutionary new idea. If matter doesn't disappear, where does it go? The answer proposed by some physicists is as audacious as it is elegant. It becomes the birth of a new universe. The new theory, a universe is born. This brings us to the heart of a new paradigm. What if black holes are the beginning? This is the central idea of a theory known as cosmological natural selection, first proposed in 1992 by physicist Lee Smolin. Smolin looked at the fine-tuning problem and saw a striking parallel to biology. In biology, complex organisms are the product of natural selection. Organisms reproduce, their offspring have random mutations, and those best suited to the environment are more likely to pass on their traits. Smolin proposed that the same logic could apply to universes. His fecund universes theory works like this. First, a new universe is born inside every black hole. When a massive star collapses, the matter doesn't hit a singularity. Thanks to quantum mechanics, it bounces. This bounce is so energetic it creates a new, expanding region of spacetime, a new Big Bang. Second, each time a new universe is born, its fundamental constants are slightly different from its parents, like a cosmic mutation. Put these two ideas together, and you get cosmic evolution. Universes whose physical laws are good at making black holes will have more offspring. Over countless generations, this process would naturally select for universes optimized for black hole production. And here's the crucial insight. The same physical constants that are good for making black holes also happen to be good for making the things that lead to us. To get lots of black holes, you need lots of massive stars. To get those, you need a universe that can form giant clouds of gas and synthesize heavy elements like carbon, the building blocks of life. In this view, the fine-tuning of our universe for life is a side effect. We live in a universe fine-tuned for making black holes, and we are simply along for the ride. But how exactly does this transition happen? This is where modern theories of quantum gravity, like loop quantum gravity, offer a stunning mechanism. The black hole transforms into its theoretical opposite, a white hole. A white hole is a hypothetical object that violently spews out matter and energy, and which nothing can enter. While classical wormholes connecting black and white holes were thought to be unstable, recent theoretical work suggests quantum effects can stabilize this bridge, allowing a transition. According to this idea, a black hole doesn't live forever. After a very, very long time, quantum effects cause it to tunnel into a white hole, beginning to release all the matter and information that ever fell in. The black hole is the womb, the quantum bounce is the conception, and the white hole is the birth, a complete story of cosmic reproduction. We are exploring the very fabric of reality here, and it gets even stranger. This isn't just abstract theory, it has profound implications for how we view our own existence. If your mind is spinning like mine is, take a second to hit that subscribe button. We explore the biggest questions in the cosmos every week. And let me know in the comments, do you think our universe was born from another? Your answer might be more than just a guess, it could be an intuition about the very nature of everything. The how painting a picture of cosmic rebirth. The idea of a universe being born from a black hole can be hard to picture. But we can use analogies. Think of a black hole as a seed. A massive star, the parent tree, spends its life gathering energy and material. At the end of its life, it produces a seed, a tiny, dense package with all the information needed to create a new tree. The black hole is that seed. The matter and energy that fall in are the genetic information. The quantum bounce is the germination, and the new, expanding universe is the sapling that grows from it. Another way to visualize it is with the rubber sheet analogy for spacetime. A star is like a bowling ball on the sheet, creating a dimple. A black hole is a weight so heavy it seems to puncture a hole in the sheet. But quantum mechanics smooths out that puncture, stretching the fabric into a deep funnel. At the bottom, the fabric is stretched to its absolute limit, and then it bounces back. But it doesn't just bounce back up into our universe. It expands outwards in a new direction, forming a separate bubble of spacetime on the other side. This new bubble is a new universe with its own space and time, connected to ours only by the quantum bridge at its origin. This framework also elegantly solves the black hole information paradox. The paradox asks what happens to the information of things that fall into a black hole. Is it erased forever? This would violate a core principle of quantum physics. The black hole to white hole theory provides a beautiful answer. The information isn't lost, it's recycled. It's passed on to the baby universe, which becomes the stored memory of everything that fell into its parent black hole. This resolves a decades-old conflict between our two greatest physical theories, turning a paradox into a mechanism for creation. The implications: a cosmos of infinite possibilities. If this theory is right, it completely revolutionizes our understanding of the universe. First, it means there was no single beginning. The Big Bang was not the Big Bang, it was just a Big Bang. Our origin story transforms from a singular event into a link in an infinite chain of cosmic generations. It suggests a multiverse not of parallel worlds side by side, but of nested, generational worlds, like a cosmic Russian doll stretching into an infinite past and future. This would be the ultimate step in decentering humanity. First, we thought the Earth was the center of everything. Then we learned it was just one planet, our sun just one star, and our galaxy just one of trillions. This theory takes the final step. Our entire universe may be just one of many in a vast, evolving cosmos. We are not special. We are a branch on a cosmic tree of unimaginable scale. The theory could also explain the arrow of time. Why does time only flow in one direction? The Big Bang started our universe in a highly ordered state. The relentless march towards disorder, or entropy, is what gives time its direction. But why was the Big Bang so orderly? The white hole birth model offers a potential answer. The expulsion naturally resets the clock, creating a fresh, low-entropy starting point for the new cosmos. Furthermore, it opens up tantalizing, though highly speculative, connections to other great cosmic mysteries. Some physicists wonder if dark matter, the invisible substance that makes up most of the matter in the universe, could be a remnant from the parent universe. Others have proposed that dark energy, the force accelerating our universe's expansion, could be fundamentally linked to the bounce mechanism that created it. These are speculative leaps, but they show the theory's incredible power, offering potential explanations for a whole host of fundamental questions about our reality. The verdict? Where's the proof? Okay, let's take a breath. As beautiful and compelling as this theory is, it is not yet proven fact. We have never directly observed a white hole, let alone the birth of a new universe. This is the frontier of theoretical physics, where ideas often run far ahead of our ability to test them. So, what would it take to move this from a fascinating hypothesis to an accepted scientific theory? The ultimate proof would require a complete and verified theory of quantum gravity. This is the holy grail of modern physics, a single framework uniting gravity and quantum mechanics. Theories like loop quantum gravity are our best attempts so far, and it is from these attempts that the bounce idea emerges. In the meantime, are there any potential clues we could look for? The answer is a tentative yes. Some physicists have suggested that if our universe was born from a rotating black hole, it might have inherited that spin, creating a subtle, preferred axis across the cosmos. This could show up as unexpected alignments in galaxy rotations or slight temperature variations in the cosmic microwave background. Another highly speculative possibility is that we could witness the final moments of tiny, primordial black holes formed in the early universe. According to some models, these could transition into white holes and erupt in a flash of energy. Some scientists have wondered if certain mysterious gamma-ray bursts could be the signature of these small bangs. These are long shots, but they represent concrete, observable predictions that could one day provide evidence for this incredible theory. We began with a mystery, a universe that appears impossibly fine-tuned for our existence. We journeyed through the standard story of cosmology, with its unexplained beginning and paradoxical end. We saw how quantum mechanics might rescue us, dissolving the dreaded infinities and replacing them with a bounce. This led us to the revolutionary idea of cosmological natural selection, a vision of a cosmic ecosystem where universes reproduce through black holes. We saw how this theory could explain our universe's apparent design as a matter of evolutionary fitness while also solving deep paradoxes. Black holes are transformed from cosmic destroyers into cosmic creators. Endings become new beginnings. What this theory offers is a narrative for our existence that is vastly more grand than we ever imagined. It tells us that the cycle of birth, life, and death may be a fundamental principle of the cosmos itself. The atoms in our bodies were forged in the hearts of stars that died long ago. Perhaps our entire universe was forged in the heart of a black hole that died in a reality we can never know. This is a theory that leaves us in a state of profound wonder. It tells us that the dark, silent voids in space, where black holes lurk, are not empty, they are full of potential. They are the wombs of future universes. And it leaves us with one final, breathtaking question. If our universe was born from a black hole in apparent reality, what kind of universe created ours? And what strange, new cosmos will one day be born from the black holes that pepper our own sky? The story of existence may not have a beginning or an end, but an infinite cosmic cycle of death and rebirth, stretching across an eternity we are only just beginning to comprehend. The impossible ingredient needed to build a wormhole. Let's talk about an idea so big it could rewrite the story of humanity. Not just our future, but our entire place in the cosmos. We're talking about shortcuts through spacetime itself, cosmic tunnels that could link our world to a star system millions of light years away. Imagine traversing the galaxy not in millennia, but in moments. This isn't just a fantasy. In a way, we have the blueprint. We have the map. But there's a catch, a problem so fundamental it makes this entire vision seem, well, impossible. The moment a wormhole is born, the universe itself seems to conspire to destroy it. Space-time works to slam the door shut, instantly and violently. To hold this cosmic gateway open, even for a single photon of light to pass through, we need a special ingredient. An ingredient so strange, so counterintuitive, it seems to break the most basic laws of physics we know. It's a substance that shouldn't exist, yet it's the one and only key. We need something called exotic matter. And the quest to understand it, find it, or maybe even create it, is one of the most tantalizing and frustrating challenges in all of science. The promise of a shortcut. To understand the problem, you first have to appreciate the sheer elegance of the idea. Wormholes aren't just a wild guess from science fiction. They pop out, almost accidentally, from our deepest theory of gravity. When Albert Einstein published his theory of general relativity in 1915, he gave us a brand new way to see the universe. Space and time weren't a static, invisible backdrop anymore. Instead, they were a dynamic, interwoven fabric, space-time. And this fabric could be bent and warped by mass and energy. A planet or a star doesn't just sit in space, it tells space how to curve. Gravity, Einstein showed us, is just the shape of space-time. For 2 decades, physicists explored the bizarre math of this new reality. Then, in 1935, Einstein and his colleague Nathan Rosen were wrestling with the idea of black holes. In an attempt to smooth out some mathematical weirdness in their equations, they stumbled onto something startling. Their math described a solution where 2 distant points in space-time could be linked by a kind of tunnel. This structure, officially an Einstein-Rosen bridge, was the very first theoretical glimpse of a wormhole. But for them, this was just a mathematical curiosity, not a plan for interstellar travel. Their wormholes would have been microscopic and would have vanished in an instant, a flicker in the cosmic code. The idea of a stable, traversable wormhole, one you could actually fly a ship through, wouldn't seriously emerge for another 50 years, thanks to physicists like Kip Thorne, who was famously inspired by a request from Carl Sagan for his novel Contact. The popular analogy for a wormhole is one you've probably seen. Imagine space-time as a sheet of paper. To get from one point to another, you have to travel across the surface, the long way. That's us right now, stuck traveling through space and limited by the speed of light. But what if you could just fold the paper, bringing those 2 distant points right next to each other? Then, you could poke a pencil through, creating a tunnel that connects them. That pencil hole is the wormhole. It's a shortcut not through space, but outside of it. You haven't broken the cosmic speed limit, you've just bypassed the distance. It's a beautiful idea. A tunnel from the Milky Way to Andromeda in the time it takes to make a cup of tea. It would make us a true galactic species. The blueprint is there, born from Einstein's genius. But the universe rarely makes things that easy. The same laws that dangle this incredible possibility in front of us are the very same laws that slam the door in our face. The universal collapse. The biggest, most immediate problem with building a wormhole is its own violent instability. An Einstein-Rosen bridge isn't a stable tunnel. It's more like a bubble in boiling water, there one moment and gone the next. If you tried to send anything through it, even a single particle of light, that particle's own energy would be enough to trigger a catastrophic collapse. Think about our tunnel analogy again, but this time, the tunnel is dug through a mountain of sand. The second you finish digging, the walls start pouring inward. Gravity is relentless. The tunnel doesn't just get smaller, it implodes. The entrance and the exit rush toward each other and smash together into a singularity, a point of infinite density where physics just gives up. And this doesn't happen slowly. For any wormhole you could actually use, this collapse would happen at nearly the speed of light. The gateway would be gone before anything could ever get through. This isn't just an engineering problem. It's a crisis rooted in the nature of gravity itself. General relativity tells us that all the energy we know, the positive energy that makes up you, me, planets, and stars, always creates attractive gravity. It pulls things together, like a bowling ball on a trampoline that makes everything else roll toward it. A wormhole is an object with an immense concentration of this energy. That energy creates a powerful gravitational pull that acts on the wormhole itself, pulling its throat, the narrowest part of the tunnel, inward from every direction. It's a destructive feedback loop. The narrower the throat gets, the more concentrated the energy becomes, the stronger gravity gets, and the faster it all collapses. A self-destruct sequence is baked right into the design. So, for decades, it seemed like a dead end. Wormholes were a cool but useless quirk of physics. But what if you could fight back against that collapse? What if you could prop the tunnel open? To do that, you'd need something that creates the opposite of attractive gravity. You'd need anti-gravity. And that means you'd need a substance so bizarre, it sounds like pure science fiction. The hero ingredient, exotic matter. To stop the wormhole from collapsing, we have to introduce our story's most important character. This is the impossible ingredient of our title, exotic matter. And frankly, the word exotic doesn't quite do it justice. Exotic matter is a theoretical substance that has one key property that nothing we've ever seen or touched possesses. It has negative energy density. Let's unpack that, because it's a concept that ties your brain in a knot. Everything you've ever encountered has positive mass and positive energy. A rock has mass. Throw it, and it has kinetic energy. Even pure energy, like light, has a positive gravitational pull. And as we said, positive energy creates attractive gravity. That's the rule. Stuff pulls other stuff together. Exotic matter breaks that rule. Its defining feature is that it generates repulsive gravity. It pushes things away. It's anti-gravity. Go back to the trampoline analogy. Normal matter is the heavy bowling ball that creates a dip everything falls into. Exotic matter would be like an anti-bowling ball. Instead of making a dip, it would create a hill, actively pushing everything away from it. Now you see why this is the key. If you could line the throat of a wormhole with this stuff, its repulsive gravity would push outward, acting like a cosmic scaffold that holds the gateway open against the crushing force of its own collapse. It would be the pillar that turns our tunnel of sand into a stable highway through spacetime, letting ships, information, and maybe even people pass through. This isn't just a hopeful guess, it's a mathematical requirement. In the late 1980s, physicists like Kip Thorne proved that for any traversable wormhole to exist, it must be threaded with matter that violates what's known as the null energy condition. That's just the technical way of saying it needs stuff with negative energy density. There's no other known way. The laws of general relativity are crystal clear on this point. To build a stable wormhole, you need exotic matter. The problem is, that ingredient doesn't seem to be for sale anywhere in the universe. Deconstructing the impossible. So what is this stuff, really? Saying it has anti-gravity is a good start, but the physics is even weirder. The main requirement comes from what has to happen to light passing through a wormhole. As a beam of light enters one mouth and travels toward the throat, the curved spacetime naturally forces the light rays to bend inward to converge. That's just standard gravitational lensing, and it's no big deal. But after passing the throat, for the tunnel to open back up on the other side, something unnatural has to happen. Those converging light rays must suddenly start to diverge, to spread apart again. According to a fundamental rule of general relativity, this just can't happen in a vacuum or in the presence of normal matter. Normal, attractive gravity only ever makes light rays converge more. It's a one-way street. To force those light rays to spread out, you need something that gravitationally repels them. You need a region of space that warps spacetime outward instead of inward. That's what negative energy does. Without the repulsive, defocusing effect of exotic matter, the light rays would all converge to a single point in the throat, creating a singularity and destroying the wormhole. Another way to look at it is through pressure. Normal matter has positive pressure. If you squeeze a gas, it pushes back. Exotic matter would need to have a huge negative pressure, a tension. Think of a stretched rubber band. Now imagine a tension so powerful it's actually greater than the energy density of the substance itself. If you could hold a chunk of it, it wouldn't push against your hands, it would try to violently pull them inward. It's this immense tension that would, in theory, pull space-time open and keep the wormhole's throat from collapsing. So our impossible ingredient has two mind-bending properties. First, negative energy density, meaning it repels gravitationally. Second, a massive negative pressure or tension. No particle in the standard model of particle physics, the theory describing all known matter and forces, fits this description. Protons, electrons, quarks, photons, none of them work. This is why building a wormhole isn't like building a better bridge. It's like trying to build a bridge out of a material that, according to the rulebook of reality, shouldn't even exist. The staggering scale of the problem. Okay, let's pretend for a minute that we've figured out how to make exotic matter. We have a machine that can churn it out. Even then, the sheer amount of it required is so astronomical it pushes the whole idea into the realm of fantasy. The calculations, first pioneered by physicists like Kip Thorne and Matt Visser, are just brutal. Let's design a modest wormhole, one with a throat about a meter wide, big enough for a person to float through. To keep this portal stable, the exotic matter can't just be anywhere. It has to be concentrated in an unbelievably thin band right at the throat, a region of subatomic thinness. The engineering precision alone is mind-boggling. But that's not the real shocker. The true jaw-dropper is the asterisk amount of negative energy you'd need to pack into that tiny ring. To stabilize our 1-meter wormhole, you would need a total amount of negative energy equivalent to the entire mass energy of a giant planet like Jupiter. Let that sink in. Not the mass of a car or a mountain, but the entire mass of Jupiter, converted into a negative form of energy. We are a species that still largely runs on burning old plants. The idea of wielding the energy of a gas giant is, to put it mildly, a bit beyond our current pay grade. And in a strange twist, making the wormhole bigger is both easier and harder. If you want a throat that's a whole light year across, a true interstellar highway, the asterisk density of the negative energy required actually goes down. That's the good news. The bad news is that the total amount of it you need goes up. And you still have to confine that energy to a region of subatomic thickness. This is the harsh reality of wormhole physics. The universe shows us this beautiful possibility but locks it behind a door with an impossible key. It demands we gather the energy of a planet and then focus it with a precision smaller than an atom. It's a challenge so immense it makes you wonder, is the universe playing a cruel joke on us? Or is there a loophole we just haven't found yet? A glimmer of hope? The Casimir effect. For a long time, negative energy was purely theoretical. The equations demanded it, but it had no known connection to the real world. But then, a subtle prediction from the bizarre world of quantum mechanics offered a tiny glimmer of hope. It suggested that negative energy isn't just a fantasy. It's real, and we've even measured it. This phenomenon is called the Casimir effect. To get it, you have to accept that empty space isn't really empty. It's a bubbling, seething soup of quantum fluctuations, where pairs of virtual particles and antiparticles constantly pop into existence and annihilate each other. This is happening everywhere, all the time. In 1948, the physicist Hendrik Casimir predicted that if you take two perfectly smooth metal plates and place them incredibly close together in a vacuum, something weird will happen. The space between the plates restricts which virtual particles can pop into existence, while the space outside has no such restrictions. This creates an imbalance, more quantum fluctuations pushing on the outside of the plates than on the inside. The result is a tiny but measurable force pushing the plates together. But the truly weird part is the space between the plates. Because it has fewer quantum fluctuations than the normal vacuum, its energy density is less than zero. It is a region of real, measurable negative energy density. This was a huge deal for wormhole theorists. The impossible ingredient suddenly seemed a little less impossible. Nature, it turns out, does allow for negative energy. However, before we start drafting blueprints, we have to face the limitations. The Casimir effect only creates a minuscule amount of negative energy in a tiny, constrained space. It's nowhere near the planetary scale energies needed to stabilize a wormhole you could actually use. Furthermore, quantum physics seems to have its own checks and balances, known as quantum energy inequalities. In simple terms, they suggest that you can have a little bit of negative energy for a short time, or an even smaller amount for a longer time, but you can't have a lot of it for a long time. The universe lets you borrow energy from the vacuum, but it seems you have to pay it back fast. So the Casimir effect is both a source of hope and frustration. It cracks the door open, but it also suggests the universe put a lock on how much of this stuff we can ever get our hands on. Okay, we are deep in some mind-bending physics here, blurring the line between what's possible and what might forever be science fiction. If your head is spinning with the implications of negative energy and shortcuts through spacetime, that's great. It's what we love to do. Explore the biggest, weirdest questions in the universe. If you want to join us on more of these journeys, take a second to subscribe. You won't want to miss where we're going next. The quantum wormhole controversy. The whole discussion took a dramatic turn in late 2022. Headlines flashed around the world claiming a team of physicists from Caltech and Google had created a wormhole in the lab. For a moment, it seemed like science fiction had become fact. So, was it true? Well, not in the way you're thinking. They didn't create a physical tunnel in spacetime. What they did was use Google's Sycamore quantum computer to simulate a highly simplified, toy model of a wormhole. This experiment was designed to explore a deep theoretical idea known as the equals EPR conjecture, which proposes that two entangled quantum particles might be equivalent to being connected by a microscopic wormhole. In their simulation, they sent a bit of quantum information into one part of their system, watched it get scrambled and seemingly disappear, and then saw it reappear, unscrambled, on the other side. They argued the dynamics of this information, tunneling, were consistent with information crossing a wormhole. It was an ingenious experiment. But science works through skepticism. Soon, other physicists began to question the interpretation. A wave of critiques pointed out that the observed behavior could be explained by much more ordinary quantum effects that have nothing to do with gravity or wormholes. They argued that the simulation was so simplified that calling it a wormhole was a serious overstatement. One peer-reviewed analysis concluded it seriously challenges the experiment's gravitational interpretation. The controversy is a perfect example of how science really works. The exciting headline is often just the first sentence in a much longer, more complicated conversation. The experiment didn't create a gateway to another galaxy in a silicon chip, but it did spark a necessary debate and push the boundaries of what we can explore with quantum computers. The impossible ingredient wasn't found in a lab. The search had to continue. Rethinking the blueprint. The absurd difficulty of making exotic matter has led many physicists to ask, what if we're using the wrong recipe? Maybe there are other kinds of wormholes that don't need this impossible ingredient at all. One promising idea involves a force we know and love, electromagnetism. What if a wormhole also carried a massive electric charge? In these charged wormhole models, the intense electromagnetic repulsion inside the throat could, in theory, do the same job as exotic matter, pushing outward against gravity to keep the tunnel stable. Some recent research suggests that in certain modified theories of gravity, a strong enough charge could reduce or even completely eliminate the need for exotic matter. That's exciting, because electric charge is real and something we can actually work with. Other researchers are exploring ideas like PT-symmetric wormholes. Without getting lost in the math, these models suggest it might be possible to build a stable wormhole where the exotic matter is confined to an infinitesimally thin layer. What's really cool is that these models might produce observational signatures, things we could actually look for, like gravitational echoes, in the signals from merging black holes. This moves wormholes from being pure theory to something we could potentially hunt for with our telescopes. And finally, some theorists are looking at the energy problem from a different angle. What if, through clever geometric engineering of the wormhole's mouth, you could get away with using an arbitrarily small amount of negative energy? These are all frontier ideas, but they show a shift in strategy, from a brute force approach of gathering impossible energies to a more elegant, geometric solution. The ultimate plot twist. Are wormholes even tunnels? We've spent all this time trying to figure out how to build a wormhole. But what if the reason it's so hard is because the universe is trying to tell us something else entirely? What if they aren't tunnels at all? This is a provocative new line of thinking that has been gaining traction. It suggests that the mathematical solutions describing wormholes might not be blueprints for a cosmic subway system. Instead, they might be clues to something far deeper about the nature of our universe, linking gravity and quantum mechanics. From this perspective, an Einstein-Rosen bridge isn't a place you can go. It's a mathematical representation of a complex quantum connection, like the one suggested by equals EPR. The reason it takes impossible ingredients to make it traversable is the universe's way of telling us, that's not what this is for. It's a form of cosmic censorship, a feature, not a bug, designed to prevent paradoxes and keep the logical structure of the universe intact. It's a humbling plot twist. It suggests our decades-long quest might have been based on a misinterpretation of what the math was trying to show us. The beautiful, elegant idea of a shortcut through spacetime might be just that, an idea. A phantom born from the incomplete mathematics of the 20th century. The impossible ingredient is impossible to find because the structure it's meant to support isn't a structure the universe ever intended to build. Our journey to find the impossible ingredient has taken us from the bedrock of modern physics to its most speculative frontiers. We started with Einstein's beautiful promise, a tunnel through spacetime. We immediately hit a wall. The universe's own laws demand that such a tunnel destroy itself instantly. The only hope was a substance from science fiction, exotic matter, with its repulsive anti-gravity. But that solution came with its own impossible price tag: the energy of a planet, focused with subatomic precision. We found a glimmer of hope in the weirdness of the quantum world, with the Casimir effect proving negative energy is real, only to find that the universe seems to ration it carefully. We saw how simulations of wormholes sparked both excitement and scientific debate, reminding us that progress comes from scrutiny, not just headlines. And after all that, we're faced with the ultimate twist: the growing suspicion that wormholes might not be tunnels at all, but mathematical signposts pointing toward a deeper, hidden reality. The story of the wormhole is a perfect illustration of how science works. It's about how a beautiful idea forces us to confront the absolute limits of what we know. The search for exotic matter has pushed us to explore the very nature of energy and the vacuum. The failure to find an easy answer has forced us to be more creative and even to ask if we've been misreading the map all along. Maybe the true value of the wormhole isn't as a future spaceship, but as a theoretical probe, a question we can ask the universe to learn its secrets. And the answer, whether it leads to the stars or to a deeper understanding of home, is a journey worth taking. Our universe is just one pulse in an infinite cosmic loop. Everything you know, this world, the sun, every star in the night sky, is said to have begun in a single moment: the Big Bang. It's the grandest story we've ever told, our scientific book of Genesis. But what if that story, as epic as it is missing its first chapter? What if the Big Bang wasn't creation from nothing, but a moment of cosmic rebirth? Imagine, for a second, that our universe is just one beat in an infinite cosmic heartbeat. A single pulse in an endless loop of death and spectacular renewal. Picture a reality where the end of one universe seeds the next. Where a black hole from a cosmos that existed long before ours transforms into a brilliant white hole, erupting to become everything we see today. This isn't just science fiction. It's a real frontier of modern cosmology, a theory that challenges the very meaning of a beginning and an end. It suggests our universe isn't a one-time event, but a single breath in the life of an eternal, cycling cosmos. The known story, the universe as we've been told. To get how radical this cosmic loop idea really is, we first have to appreciate the reigning champion of creation stories, the Big Bang Theory. And it's more than just a theory, it's a monumental achievement, a story pieced together from decades of painstaking observation, brilliant math, and the relentless curiosity of scientists staring into the void and demanding answers. The story starts about 13.8 billion years ago. In that beginning, the universe wasn't empty. It was unbelievably hot and packed into an infinitesimally small point, holding all the energy and potential that would ever exist. This is the moment we call the singularity, a concept we'll come back to, because it holds the key to this whole mystery. From that single point, the universe started expanding. And this wasn't an explosion like a bomb going off in space. It was the expansion asterisk of space itself. In the first tiny fractions of a second, the cosmos went through a mind-bendingly fast growth spurt called inflation, swelling from smaller than an atom to the size of a grapefruit almost instantly. As space expanded, it cooled. The primordial soup of pure energy started to form the first building blocks of everything. Quarks, electrons, photons, all dancing in a searing hot plasma. After a few minutes, quarks began sticking together to form the first protons and neutrons. But for another 380,000 years, the universe was a dense, hot fog. Light particles, the photons, were trapped, constantly bouncing off electrons, unable to travel. The cosmos was dark. Then came a turning point called recombination. The universe cooled just enough for protons and electrons to bind together, forming the first stable atoms, mostly hydrogen and helium. Suddenly, the fog cleared. The photons were set free, and the universe became transparent. Those very first photons have been traveling across the cosmos ever since, stretched by the expanding space into long, cool microwaves. We detect them today as a faint glow in every direction we look. This is the cosmic microwave background, or CMB. It's the afterglow of creation, the Big Bang's smoking gun. From there, it's a story of gravity's patient work. Over hundreds of millions of years, tiny differences in the density of that primordial gas, the slight temperature wobbles we see in the CMB, started to grow. Denser regions pulled in more matter. These cosmic nurseries grew into huge clouds of gas that eventually collapsed under their own weight to light up the first stars. These first stars were giants, hundreds of times more massive than our Sun, and they lived fast and died young, exploding as brilliant supernovae. In their fiery deaths, they forged heavier elements, carbon, oxygen, iron, all the stuff needed for life, and scattered them across the cosmos. These elements mixed with the gas and dust that would form the next generation of stars and planets. Galaxies formed and merged, woven together by gravity and a mysterious scaffolding of dark matter. In a quiet spiral arm of one of these galaxies, the Milky Way, a cloud of gas and dust collapsed to form our Sun, and around it, a rocky little world called Earth. This is the story of the Big Bang. It's backed by a mountain of evidence, from the way distant galaxies are rushing away from us, proving the universe is expanding, to the exact amounts of light elements we see in the cosmos, which match the theory's predictions perfectly. It's a beautiful, powerful, and largely correct story of our history. But it's not complete. It tells us how the universe evolved, but it falls silent on the biggest question of all: why? The cracks in the cosmic egg, the puzzles of the beginning. Even the best scientific theories have their limits, the frayed edges where our understanding just stops. For the Big Bang model, these aren't small details. They're fundamental puzzles that hint at a deeper, stranger reality. The first and biggest crack is the singularity itself. The theory tells us that if you rewind the universe, everything squeezes into a single point of infinite density and temperature. But in physics, infinity isn't a real answer. It's what you get when your equations break. It's a stop sign. Our current laws of physics, including Einstein's theory of general relativity, completely fall apart at this point. They can't tell us what the singularity is, or what came before it. This leaves us with a huge paradox: the problem of a beginning. If the Big Bang was the start of time itself, what does "what happened before the Big Bang" even mean? It's like asking what's north of the North Pole. The Standard Model offers no answer, just a wall our science can't see past. It implies creation out of nothing, ex nihilo asterisk, which is a deeply unsatisfying idea for physicists who live by cause and effect. Where did all the energy come from? What lit the fuse? The second crack is the flatness problem. Think about trying to balance a pencil perfectly on its sharp tip. The slightest error, and it falls. The geometry of our universe is like that pencil. Our best observations show that the universe is astonishingly flat. That just means on the biggest scales, it follows the geometry we learned in school: parallel lines stay parallel. For the universe to be so perfectly flat today, after 13.8 billion years of expansion, its density in the first moments had to be fine-tuned to an insane degree. We're talking accurate to 1 part in 10 to the 60th power. That's like measuring the distance to the nearest star and being off by less than the width of a human hair. If the density had been a tiny bit higher, the universe would have already collapsed in a big crunch. A tiny bit lower, and it would have expanded so fast that stars and galaxies never could have formed. The Big Bang model doesn't explain why it started with this perfect, life-permitting balance. It just was. The third crack is the horizon problem, and this one is a real head-scratcher. When we look at the cosmic microwave background, it's almost perfectly uniform in temperature everywhere we look. The ancient light from one side of the sky is almost the exact same temperature as the light from the complete opposite side. This doesn't sound like a big deal until you remember how huge the universe is. These two regions of space are so far apart that there's no way they could have ever been in contact. No signal, not even one traveling at the speed of light, could have possibly passed between them to even out their temperatures. It's like finding two pots of water on opposite sides of a continent boiled to the exact same temperature at the same time, without any communication. How did they coordinate? To solve these problems, cosmologists came up with the idea of inflation, that hyper-fast expansion in the first second. Inflation suggests the whole universe we see was once a tiny, connected patch that was all one temperature before it got stretched out. This stretching would have also flattened its geometry. It's a brilliant patch, but some argue it just adds another layer of mystery we can't explain. These puzzles, the singularity, the flatness, the horizon, are clues. They tell us our story is missing something important. They suggest the Big Bang might not have been the absolute beginning, but just one moment in a much grander cosmic drama. The challenger emerges. A universe without a beginning. When your best theory leads you to a wall of infinities, maybe you're looking at the problem the wrong way. That's the thinking behind a new class of models known as bounce cosmology. They all share a revolutionary idea. The Big Bang wasn't a beginning from nothing. It was a rebound. Imagine dropping a rubber ball. It falls, hits the ground, and for a split second, all its downward motion is converted into compressed energy. Then, that energy is released, and the ball bounces back up. In this analogy, a contracting universe is the ball falling. A point of maximum density is the ground. And the Big Bang is the bounce. This simple idea changes everything. It gets rid of the singularity. In a bouncing universe, the cosmos doesn't collapse to an infinite point. Instead, it reaches a point of incredible, but finite, density, before some new physical principle kicks in and reverses the collapse into an expansion. The question, what came before the Big Bang, suddenly has an answer. A previous, contracting universe. But what could be powerful enough to reverse the collapse of an entire universe? The answer seems to lie where our current laws fail: the quantum world. The engine of the bounce is thought to be quantum gravity. At the unbelievably small scales and high energies of a collapsing universe, physicists believe spacetime itself must be made of discrete, indivisible units, like pixels on a screen. One leading idea is called loop quantum cosmology, or LQC. In LQC, the fabric of space has a sort of atomic structure. This graininess creates a new repulsive force at extreme densities. As the universe contracts, the atoms of spacetime get squeezed, creating an outward pressure so immense it overwhelms gravity and powerfully flings the universe back outward in a big bounce. The singularity is avoided because spacetime can't be crushed to zero. There's a smallest possible volume, and once you hit it, you have to bounce back. This leads to an even more stunning version of the theory, one that connects the bounce to black holes and their theoretical opposites, white holes. In this scenario, the previous universe collapsed into what was essentially one giant, universe-sized black hole. A black hole is a one-way door from which nothing can escape. But what if the singularity inside isn't an endpoint, but a gateway? Enter the white hole, the perfect time reversed twin of a black hole. Its event horizon is a door that only opens one way, out. Matter and energy can only erupt from a white hole. Nothing can ever get in. For decades, they were just a mathematical curiosity. But recent theoretical work is breathing new life into them. The new thinking suggests that because quantum information can't be destroyed, a black hole must eventually transform, releasing everything it ever consumed. The proposed solution? The black hole undergoes a quantum transition into a white hole. In this breathtaking picture, our Big Bang was the eruption of that primordial white hole. Matter and energy from the collapsed previous universe were funneled through this black hole to white hole gateway and violently ejected to form our new, expanding cosmos. Some physicists even speculate that this process could be linked to the origin of time itself. In some of these advanced models, time isn't a static backdrop. It emerges and flows, beginning its journey at the white hole's eruption. What we feel as the flow of time could be a direct consequence of the universe's expansion, which began at the bounce. This thinking tries to connect three of the biggest mysteries in physics, the Big Bang, black holes, and dark energy, into one cohesive story. The grand cosmic loop, a symphony of cycles. If the Big Bang was a bounce, it begs the question, was the universe before ours the first? Or was it also born from a bounce? This is the gateway to the grandest vision of all, the cyclic universe. In this model, the cosmos is eternal, locked in an endless waltz of expansion and contraction, death and rebirth. Our universe is just one pulse in an infinite cosmic symphony. The simplest version is the old, Big Crunch model. If there's enough stuff in the universe, gravity should eventually win out over the expansion. Like a ball thrown in the air, the universe would slow down, stop, and then start falling back in on itself, ending in a fiery Big Crunch, a mirror image of the Big Bang. From there, a bounce could start the next cycle. For a long time, this idea was out of fashion. In the late 90s, astronomers discovered the expansion is actually accelerating. This pointed to a mysterious force called dark energy pushing everything apart. For years, it seemed to sentence our universe to a big freeze, a future where it expands forever until it's a cold, dark, empty void. The cycle, it seemed, was broken. But the story of dark energy might be getting a rewrite. While most data is consistent with a constant dark energy leading to a big freeze, some puzzling observations have inspired new theoretical models. In some of these speculative scenarios, dark energy isn't a constant force. It could be a field that decays over time, or even switches from repulsive to attractive. If that's true, the Big Crunch is back on the table. For example, one model proposed to fit some of this data suggests our universe could keep expanding for another 11 billion years, peak, and then, as dark energy fades, gravity would take over, initiating a collapse that ends in a Big Crunch roughly 20 billion years after that. This is highly speculative, but it has dramatically resurrected the possibility of a cyclic universe. This has reinvigorated fascinating models like conformal cyclic cosmology, or CCC, from the renowned physicist Sir Roger Penrose. In his vision, the universe expands for trillions of years into that big freeze. Eventually, everything dissolves into a vast, empty sea of photons. Here's the genius part. In a universe with only massless photons, concepts of time and distance become meaningless. The infinitely large, cold end of one universe becomes mathematically identical to the infinitely small, hot beginning of the next one. The end of one eon, as Penrose calls it, seamlessly becomes the Big Bang of the next. He even claimed to find evidence in the CMB, faint circles he calls Hawking points, echoes of black holes from the previous eon. It must be said, this is a very bold claim, and many physicists remain deeply skeptical, noting that there's no conclusive statistical evidence for these spots. Other models, born from string theory, imagine our universe as a 3D brane, floating in a higher dimension. The Big Bang is caused by our brane colliding with another one, periodically resetting the cosmos. Recent theoretical work in string theory has also explored concepts like instant folded strings that could theoretically enable a cosmological bounce. So, let's picture one full loop. We start now, 13.8 billion years in. Galaxies fly apart. If the cycling model is right, this continues for maybe 11 billion more years. Then, a turning point. Dark energy weakens, gravity wins. The expansion halts. Then, the Great Contraction begins. Galaxies rush toward each other. The sky blazes with light. Stars and planets are ripped apart into a contracting fireball, the Big Crunch. But it doesn't end. At the breaking point, quantum gravity pushes back. The universe bounces. A new Big Bang erupts, and a new 13.8 billion year clock starts ticking. The unanswered questions and cosmic hurdles. As beautiful as this idea is, we have to be honest. This is a frontier theory, not established fact. It solves some of the Big Bang's problems, but it creates new ones. The biggest is the entropy problem. The second law of thermodynamics says that disorder, or entropy, always increases in a closed system. The universe is a closed system. A broken egg never unscrambles itself. So, if the universe goes through cycles, each cycle should create more entropy. That means each new universe would start out messier and less ordered than the one before it. The cycles would get longer and longer. If you run that backward, you eventually hit a first, perfectly ordered cycle. You've just replaced the problem of a first singularity with the problem of a first, perfectly ordered state. It reintroduces the beginning that the theory was trying to avoid. The second hurdle is the lack of a smoking gun. The Big Bang theory is supported by hard evidence. Bounce cosmology doesn't have that yet. The idea of a black hole to white hole transition is fascinating, but we've never seen a white hole. They're completely theoretical. We can't see past the cosmic microwave background to glimpse a universe before ours. That doesn't mean evidence is impossible. Scientists think the bounce could have left specific, subtle imprints on the CMB. Others hope that future gravitational wave observatories might detect the faint whispers of a pre-Big Bang contracting phase. Finding that would be like hearing the ghost of a universe that once was. But for now, these searches have come up empty. Finally, there's the white hole problem itself. In classical physics, white holes are seen as incredibly unstable. It's only through the lens of modern, unproven quantum theories that they become a possibility. The very heart of the most compelling bounce models is built on physics we don't fully understand yet. So, while the story of the cosmic loop is captivating, it's a story that's still being written. It provides incredible answers to old questions, but it asks new, difficult ones of its own. If these ideas are stretching your imagination, if you find yourself staring up at the night sky and wondering what's really going on out there, you're in the right place. These are the questions that drive science forward. If this kind of cosmic mystery is what you live for, make sure you subscribe and ring that notification bell. We're all on this journey of discovery together, and the biggest questions are still waiting for us. We are at a fascinating crossroads. For a century, we've lived with the Big Bang, a theory that gave us a history and a moment of creation. But now, we're glimpsing a reality that might be far older and larger. The idea that our universe is just one pulse in an infinite loop changes everything. It suggests the Big Bang wasn't our origin, but simply our dawn. It reframes our universe not as a one-off miracle, but as part of a natural, eternal recycling process. The atoms in your body, forged in the hearts of stars, might be even more ancient than we thought. They could be the recycled relics from countless universes past, stardust that has seen the birth and death of realities we can only dream of. Our existence might not be the main event, but one line in an epic poem with no beginning and no end. This theory is speculative, and it might be wrong. But its power is in the questions it makes us ask. It pushes the boundaries of our imagination and reminds us that reality is almost certainly stranger and more magnificent than we can currently comprehend. So the next time you look at the stars, consider that you might not be looking at the aftermath of a single explosion, but at one fleeting moment in an infinite, breathing cosmos. And that leaves us with one last, awe-inspiring thought. If our universe is just one link in an infinite chain, what wonders, what kinds of life, what laws of physics might have existed in the eons before ours? And what unimaginable new realities will emerge in the eons yet to come? The universe's biggest secret explained while you sleep. Tonight, as the world outside grows quiet, we'll drift into a cosmic story. A story about an end that might not be an end at all. Come, let your mind settle. Let your breathing soften. There's nothing to do right now but listen. We're going to travel to the edge of our understanding, to a place where space and time themselves seem to fray, and ask a gentle, cosmic question. What if the universe's most mysterious objects, black holes, aren't cosmic graveyards? What if, instead, they're the seeds of a new beginning? Tonight, we'll explore this possibility. Not with sudden shocks or complex equations, but as a slow story, told to the rhythm of your own restful breath. We'll journey together into the heart of a black hole, past the point of no return, and imagine what happens as it holds onto its secrets. And then, we'll imagine it performing an incredible magic trick. A spectacular cosmic bounce, flipping from a black hole into its opposite, a white hole, in a silent, brilliant flash that could birth a new universe. This is a story that suggests a kind of cosmic recycling, where information is never truly lost, and time doesn't just end, but perhaps begins again. So find a comfortable stillness, close your eyes if you wish, and let the gentle current of this cosmic river carry you into the deep. The familiar unknown, black holes. Let's begin with something you already know, something you've likely heard of, whispered in documentaries and science fiction. A black hole. The name itself is a masterpiece of poetry and dread. A hole in the fabric of the cosmos, one that's perfectly, utterly black. But they aren't holes, not really. And they don't suck things in like a vacuum cleaner. They are more like places. Regions of space-time where the story of gravity has reached its most dramatic conclusion. Imagine a star, one far, far more massive than our own sun. For millions, or even billions, of years, it burns with a furious light. It's a factory of creation, fusing simple atoms into heavier ones in its core, forging the very elements that might one day become planets or people. Inside this star, there's a constant, epic battle. The outward push of nuclear fusion, the explosive energy of its internal furnace, is perfectly balanced by the inward pull of its own immense gravity. For most of its life, this balance holds. The star is stable, a shining beacon in the cosmic night. But all fires eventually run out of fuel. Sooner or later, the star's core grows cold and quiet. The outward push of fusion falters, and then it stops. In that instant, the battle is over. Gravity, the silent, patient force that has been waiting all this time, wins a final, crushing victory. The star's outer layers are often blasted away in a supernova, a final, glorious firework display. But the core, the heart of the star, collapses in on itself with unimaginable violence. In a fraction of a second, a mass many times that of our sun is squeezed into a space smaller than a city, then smaller than a mountain, then smaller than a grain of sand. The collapse continues, relentlessly, until all that matter is crushed into a point of theoretically infinite density. This is what physicists, using Einstein's theory of general relativity, call a singularity. A place where our understanding of space, time, and the laws of physics simply breaks down. Around this impossible point, a boundary forms, as invisible as it is absolute. This is the event horizon. It's not a surface you could touch, it's a threshold in space-time. It is the line where the gravitational pull becomes so strong that the escape velocity, the speed you'd need to break free, exceeds the speed of light. And since nothing in the universe can travel faster than light, nothing that crosses the event horizon can ever come back. Not a spaceship, not a planet, not a particle, not even a beam of light. Everything that falls in is pulled inexorably toward the singularity at the center, its information, its history, seemingly erased from the universe forever. This is the classic picture of a black hole. A one-way trip to oblivion. A place where matter, energy, and even time itself come to an end. For a long time, this was the end of the story. A beautiful, terrifying, and final chapter in the life of a massive star. It's a lonely image, one of cosmic finality. But as we continue our journey tonight, we'll find that the universe is rarely so simple or so final. The story doesn't end here. In fact, this is just the beginning. The cosmic paradox, information and endings. Now, let your mind drift with this idea of an ending. In our everyday world, things don't truly vanish. If you burn a piece of paper, it turns to ash and smoke. The form is changed, but all the atoms, all the fundamental information that made up that paper, still exist. They've just been rearranged. This is a core principle of physics. Information, at its most basic level, cannot be destroyed. It can be scrambled, hidden, or transformed, but it's never, ever lost. This is a law that seems as fundamental as gravity itself. And yet, black holes presented a profound challenge to this idea. They seem to be the universe's perfect shredders. When a star collapses, it carries with it a universe of information, its spin, its chemical composition, its magnetic fields, its entire history. When an encyclopedia falls into a black hole, all the knowledge contained within its pages falls in with it. According to the classical picture, all this intricate detail is crushed at the singularity, lost forever. The only things a black hole was thought to remember were its total mass, its spin, and its electric charge. Everything else was wiped clean. This created a deep and troubling contradiction, a puzzle known as the black hole information paradox. It placed two pillars of modern physics, general relativity, which describes gravity and black holes, and quantum mechanics, which insists that information must be conserved, in direct opposition. For decades, physicists wrestled with this problem. Does one of the theories break down? Or is there something we're missing about the nature of black holes? The plot thickened in the 1970s, with the work of Stephen Hawking. He showed that when you apply the rules of quantum mechanics to the edge of a black hole, something strange happens. Black holes aren't perfectly black after all. They should glow, ever so faintly, with a unique kind of energy now known as Hawking radiation. Imagine the vacuum of empty space. It's not truly empty. It's a roiling sea of virtual particles, pairs of particles and antiparticles that pop into existence for a fleeting moment before annihilating each other and disappearing again. This happens everywhere, all the time. But right at the edge of a black hole's event horizon, something different can occur. A pair of virtual particles can be created, and before they have a chance to annihilate, one of them might fall into the black hole, while the other escapes into space. From the perspective of an outside observer, it looks as if the black hole has just emitted a particle. This escaping particle carries away a tiny amount of energy, which it must borrow from the black hole's mass. The result is astonishing. Black holes are not eternal. They evaporate. But this evaporation is a process of almost unimaginable slowness. A black hole the mass of our Sun would take far, far longer than the current age of the universe to evaporate completely. A supermassive black hole at the center of a galaxy might take an amount of time so vast it dwarfs the lifespan of every star that has ever or will ever shine. Still, the principle remains. Given enough time, a black hole will radiate away its mass until it shrinks, and finally, vanishes in a final puff of radiation. And here, the paradox became even sharper. Hawking's original calculations suggested that the escaping radiation was thermal and random, carrying no information about what fell in. If true, this would mean that when the black hole is finally gone, the information it swallowed is truly gone from the universe, violating a sacred law of quantum mechanics. It's as if you burned a library, and the smoke that rose carried no trace of the words written in the books. This can't be. The universe, it seems, doesn't like to forget. Today, many physicists believe the information does escape, subtly encoded in the Hawking radiation through complex quantum connections. But another, even more dramatic solution has been proposed, one that doesn't just tweak the picture but turns it completely inside out. The mirror image, introducing white holes. As you continue to breathe slowly, peacefully, let's play a game of cosmic symmetry. Imagine you have the equations of Einstein's general relativity written down before you. The elegant mathematics that describe how matter and energy bend the fabric of spacetime. These are the equations that predict black holes. Now, what if we take these equations and, just for a moment, run them backward in time? If you run the film of a collapsing star backward, you wouldn't see matter falling in, you'd see it exploding out. If you reverse the flow of time at the event horizon, a boundary you can't escape from becomes a boundary you can't enter. What you're left with is the perfect, time-reversed twin of a black hole. An object known as a white hole. A white hole is a theoretical region of spacetime that's the exact opposite of a black hole. While nothing can escape from a black hole's event horizon, nothing can enter a white hole's. It is a source, not a sink. A place from which matter, energy, and even light can burst forth, but into which nothing can ever fall. It's a cosmic fountain, a one-way street leading out, just as a black hole is a one-way street leading in. For a long time, white holes were considered little more than a mathematical curiosity, a strange artifact of the equations that probably didn't exist in the real universe. After all, how would one form? A black hole has a clear and natural formation process, the collapse of a massive star. A white hole, in the classical world of Einstein, would have had to exist since the beginning of time, spewing out matter from the very moment of the Big Bang. It seemed unlikely, a solution in search of a problem. Physicists played with ideas about them, but the white hole remained a ghost in the machine of physics, a beautiful but seemingly irrelevant idea. But what if they are more than just a ghost? What if they are a key part of the puzzle? What if the final fate of a black hole isn't to evaporate into nothing, but to transform into its opposite? This is the secret we're slowly unraveling tonight. The idea that these two cosmic opposites aren't separate entities, but two phases of a single, incredible life cycle. That the end of the black hole's story is the beginning of the white hole's. And to understand how that could be possible, we have to go deeper, past the world of Einstein, into a realm where spacetime itself is not what it seems. A new kind of fabric, loop quantum gravity. To bridge the gap between a black hole and a white hole, between an ending and a beginning, some physicists believe we need a new kind of physics. We need a theory that can unite the two great pillars of modern science: Einstein's general relativity, the theory of the very large, and quantum mechanics, the theory of the very small. For decades, this has been a holy grail of theoretical physics. One of the most promising candidates for this unified theory is called loop quantum gravity. And it tells a story about the fabric of our universe that is strange, beautiful, and profound. Imagine spacetime, the four-dimensional canvas of our universe, not as a smooth, continuous sheet of fabric, but as a woven cloth. If you look at it from a distance, it appears perfectly smooth and seamless. But if you could zoom in, closer and closer, down to an impossibly small scale, you'd see that it's actually made of discrete threads, tiny, indivisible loops. This is the central idea of loop quantum gravity, or LQG for short. It suggests that spacetime isn't infinitely divisible. There's a smallest possible unit of space, a quantum of volume. You can't have a space smaller than this fundamental pixel. This smallest possible scale is known as the Planck scale, an unbelievably tiny dimension where the strange rules of the quantum world take over. At this level, spacetime is no longer smooth, but chunky, made of these interconnected loops or spin networks. This seemingly simple idea has a staggering consequence. It completely changes the story of what happens at the center of a black hole. In Einstein's theory, the collapsing matter of a star is crushed into a singularity, a point of zero volume and infinite density. But in loop quantum gravity, this is impossible. You can't have a point of zero volume, because there's a minimum, fundamental unit of space. The collapse must stop somewhere. Think of it like this. Imagine you're compressing a sponge. You can squeeze it smaller and smaller, but you can't squeeze it down to nothing. Eventually, the material of the sponge itself pushes back. In the world of LQG, spacetime itself has this property. As the matter inside a black hole is crushed, the density increases to an unimaginable degree. But just as it approaches the point where a singularity would form, something new happens. The quantum structure of spacetime itself begins to push back. According to this theory, a new force, a powerful repulsive force that only exists at these extreme, Planck-level densities, awakens. This quantum pressure resists the pull of gravity, halting the collapse. The heart of the black hole doesn't get crushed into an infinitely dense point. Instead, it's squeezed into an object of maximum possible density, a state theorized to be a Planck star. It is an object of almost unimaginable density, but it is finite. It has a size, and because it's finite, it doesn't break the laws of physics. There is no singularity. In this picture, loop quantum gravity would heal the broken heart of a black hole, replacing the terrifying, law-breaking singularity with a predictable, physical object. A place where time and space were meant to end is now just a place of extreme physics. An ending has been averted. But what happens next? What happens to this incredibly compressed Planck star, held in a delicate balance between crushing gravity and quantum repulsion? It doesn't stay there forever. It waits. And then, it might just bounce. The quantum bounce, a possible secret. Here we arrive at the heart of our story, at what some physicists think could be the universe's biggest secret. That Planck star, which the theory says forms at the core of the black hole right after it collapses, is not a static object. It's a turning point. It's the moment a fall could become a launch. The idea is called the quantum bounce. In the quantum world, objects can do things that seem impossible in our everyday experience. A particle can be in multiple places at once. It can also, through a process called quantum tunneling, pass through a barrier that it shouldn't have enough energy to overcome. It's like a ghost walking through a wall. And this is precisely what some loop quantum gravity models predict will happen to the core of the black hole. The incredibly dense Planck star, under the immense pressure of its own gravity, performs a quantum tunnel. It doesn't explode in the conventional sense. Instead, the theory suggests the entire geometry of spacetime inside the black hole flips. The inward pulling, trapped region of the black hole tunnels through an impossible state and emerges as its opposite, an outward pushing, anti-trapped region. In that instant, a black hole could become a white hole. This transformation isn't something that would happen in space and time. It would be a transformation of space and time. Time itself, which for an object falling into a black hole seems to lead only to a dead end, would find a new path forward. It would bounce. The collapse would be reborn as an expansion. The cosmic drain would become a cosmic fountain. And what about all the matter and information that fell into the black hole over its long life? The star that formed it, the dust, the gas, the unfortunate encyclopedias? They wouldn't be destroyed at a singularity. They would be compressed, stored, and preserved in the Planck star at its core. Think of it as the universe's most efficient hard drive. All that information is held in a state of suspended animation, waiting for the bounce. When the black hole to white hole transition occurs, all of that stored matter and energy is released. It's ejected from the new white hole in a rapid, explosive burst. This would solve the information paradox in a beautifully elegant way. The information isn't lost, it was just delayed. It falls into a black hole, waits for an incredibly long time, and then re-emerges from a white hole. The universe, in this story, never forgets. It just has a very, very long memory. So the picture is now complete. A massive star collapses, and at its heart, a tiny, ultra-dense Planck star forms immediately, surrounded by an event horizon. The black hole lives its life, but over an immense timescale, something incredible is waiting to happen. An ending could become a beginning. A cosmic graveyard could become a cosmic nursery. The cycle could be complete. But there is one final, mind-bending piece to this puzzle: the question of time. The cosmic timescales, a story of patience. As you rest here, in the quiet of this moment, think about the passage of time. A minute, an hour, a day. Our lives are measured by these gentle, rhythmic cycles. The universe, however, operates on a scale that defies human comprehension. The story of a black hole's bounce is a story of cosmic patience, played out over timescales so vast they make the age of the universe seem like the blink of an eye. Let's consider a black hole born from a star just a few times more massive than our Sun. From an outsider's perspective, this black hole will sit in the darkness of space for an almost unimaginable stretch of time. Due to the extreme warping of time near a black hole, a process that might feel quick for the object itself is stretched out over eons for the rest of the universe. The time it takes before the bounce is visible to a distant observer is staggeringly long. For a black hole with the mass of our Sun, the wait is estimated to be around 10 to the power of 67 years. Let's try to wrap our minds around that number. It's A1 followed by 67 zeros. The current age of the universe, from the Big Bang until now, is roughly 13.8 billion years, or about 10 to the power of 10 years. The time until a bounce is not just millions or billions, or trillions of times longer than the age of our universe. It is a number so colossally large that it's almost meaningless. The black hole waits. It sits in the silent darkness of a future, empty universe, long after the last stars have burned out. It waits patiently for eons that are beyond any human or cosmic measure. And then, after all that waiting, the bounce itself happens. How long does the transition from a black hole to a white hole take? An instant. The bounce is a quantum process, and it's thought to occur on the Planck timescale, about 10 to the power of minus 43 seconds. An amount of time as infinitesimally short as the waiting period was long. There's a profound asymmetry here. An almost eternal wait, followed by a fleeting, momentary existence as a white hole as it explodes and disappears. It's like waiting for a mountain to erode, grain by grain, over billions of years, only for the final grain to vanish in a flash of light. This vast timescale might seem to make this idea a mere theoretical curiosity. If we have to wait that long, will we ever see one? Perhaps we don't have to. Some theories suggest that tiny, primordial black holes could have been formed in the fiery chaos of the Big Bang itself. These smaller black holes would have a much shorter lifespan. According to some calculations, primordial black holes of a certain mass could be bouncing right now, releasing their stored information in flashes of high-energy particles. These fireworks could be detectable, faint whispers from the dawn of time, telling us that this cycle of cosmic rebirth might just be real and ongoing. The search for these signals is one of the most exciting frontiers in modern physics. The grand vision, our universe's origin? And now, as we drift toward the end of our journey, let's take this incredible idea, the quantum bounce of a single black hole, and scale it up to the grandest stage of all, the origin of our own universe. The standard story of our universe begins with the Big Bang, a moment where everything, all of space, all of time, all of matter and energy, burst forth from a single, infinitely hot and dense point, a singularity. But we've learned tonight that some theories, like loop quantum gravity, don't like singularities. They replace them with bounces. So, what if the Big Bang was not the beginning of everything? What if the Big Bang was actually a big bounce? This is perhaps the most profound and awe-inspiring implication of this entire line of thinking. Imagine a universe that existed before ours. A vast, ancient cosmos, perhaps not so different from our own. It lived its life, stars shone and faded, galaxies formed and drifted apart. But eventually, this parent universe may have stopped expanding and began to contract, falling back in on itself in a big crunch. All the matter and energy of that universe would collapse, faster and faster, into an ever denser state. According to classical physics, it would all end in a final, universe-ending singularity. But with the rules of quantum gravity in play, we can imagine a different story. As the density of the collapsing universe reached the Planck scale, the repulsive force of quantum spacetime could kick in, just as it did in the heart of our black hole. The collapse would halt. The universe would not be crushed into nothingness. It would reach a point of maximum compression, and then, it would bounce. Our Big Bang, in this picture, was the moment of that cosmic rebound. There's another, even more mind-bending idea, related but distinct. What if our universe wasn't born from the collapse of a whole other universe, but from the collapse of a single, supermassive black hole within it? In this scenario, we could be living in a universe that is, from the perspective of an outside observer in a higher dimension, contained entirely within a black hole. This paints a picture of a fractal-like cosmos, where universes are nested within one another like Russian dolls. Whether our universe was born from a big bounce or from the heart of a black hole, the philosophical implication is the same. The universe may be eternal. There may have been no absolute beginning, and there may be no final end. Just an endless, graceful cycle of existence. We might not be the first chapter of the story. We may simply be the latest. This journey we've taken tonight, from a single collapsing star to the birth of our entire cosmos, is a testament to the power of human curiosity. It's a story spun from mathematics and imagination, a story that is still being written at the very edge of what we know. If you found a sense of calm and wonder in this cosmic tale, perhaps you'd consider subscribing for more gentle journeys into the mysteries of the universe. There's no pressure. The goal here is simply to create a quiet space for thought and relaxation. Your presence is what matters most. And if you feel moved to, please share your own thoughts in the comments below. What part of this story resonated with you? Does the idea of a bouncing universe bring you a sense of peace? Every thought adds to the shared wonder. Drifting into wonder. So, as we settle back now, let the ideas we've explored tonight gently dissolve into the quiet of your mind. We began with the image of a black hole as a terrifying, final end. A cosmic monster that devours light and time. But we've transformed it, step by slow step, into something else entirely. We've seen it as a keeper of information, a patient guardian of secrets held for eons. We've seen it as a potential cosmic parent, a gateway to a spectacular rebirth. The universe's biggest secret might just be that there are no true endings, only transformations. No dead ends, only new beginnings. The matter that makes up your body, the atoms forged in the heart of ancient stars, may have lived through countless cosmic cycles before this one. They may have fallen into a black hole in a universe long past, waded through an unimaginable eternity, and been reborn in the flash of a white hole that we call our Big Bang. Sleep on that thought. Let it cradle you. The universe may not be a place of random violence and eternal loss, but perhaps one of endless, graceful recycling. A place where even the darkest, most mysterious objects are not points of annihilation, but promises of renewal. Tonight, as you drift into your dreams, perhaps you can imagine your own consciousness tunneling through the darkness, not to an end, but to a bounce. To a new beginning, waiting on the other side of silence. Rest well. The universe's most violent object is a raging white hole. Forget what you think you know about cosmic violence. Forget supernovas that tear stars apart or galaxies colliding in a slow dance of destruction. The true titan of cosmic rage might not be a silent devourer or a creeping, inevitable void. It might not be the black hole. What if the most violent object in the universe isn't what swallows worlds, but what births them in a furious, unimaginable explosion? This is a theoretical object, a ghost in the equations of physics, known as a white hole. And tonight, we're opening a cold case. We're going on a hunt that interrogates the very fabric of space and time and asks a question that could rewrite the story of our universe. Are these cosmic volcanoes real? And could one be hiding in plain sight? We live in a cosmos defined by a dramatic tension, a constant push and pull between creation and destruction. And for most of the last century, the heavyweight champion of cosmic destruction has been the black hole. We know them well. They're the universe's apex predators. Formed from the collapsed corpses of colossal stars, they are points of such intense density and unforgiving gravity that nothing, not even light, can escape their grasp. They are the ultimate cosmic prisons, silent and patient, warping spacetime around them. We've seen their shadows, the dark silhouettes they cast against the bright tapestry of the cosmos, a final scream of light from matter spiraling into the abyss. They're a well-established, terrifying, and awe-inspiring part of our reality. But what if these cosmic monsters have a twin, an opposite, a reflection born from the very same mathematics that first predicted their existence? If a black hole is a one-way door to oblivion, its twin is a one-way street out. It's an object you can never, ever enter, no matter how hard you try. Instead of pulling everything in, it violently, relentlessly, and cataclysmically spews everything out. This isn't a gentle leak. It's a raging, cosmic volcano, an object of such ferocious power it could make a supernova look like a flickering candle. This is a white hole, and it is, hypothetically, one of the most violent objects the universe could ever conceive. For decades, they were dismissed as a mathematical fantasy, a solution to Einstein's equations that nature would never build. But now, a vanguard of physicists armed with a new understanding of the quantum world are reopening the case. They are suggesting that white holes aren't just a fantasy. They might be the secret to understanding everything from the birth of our universe to the mysterious nature of dark matter. So, join me as we journey to the other side of the horizon, to explore a place where time can run backwards and the laws of physics are turned inside out. We'll dissect what a white hole is, visualize its spectacular behavior, and hunt for clues of its existence in the darkest corners of the cosmos. By the end of this journey, you'll be questioning whether the Big Bang was truly a beginning, and whether the end of a black hole is an end at all. The familiar villain, understanding the black hole. Before we can appreciate the sheer theoretical violence of a white hole, we need to set the stage with its more famous sibling, the black hole. At its core, a black hole is simplicity itself. It's what happens when you cram an enormous amount of mass into an impossibly small space. For stellar mass black holes, the story begins with the death of a truly massive star, one at least 20 to 30 times more massive than our Sun. Throughout its life, this stellar titan is a battleground. Nuclear fusion in its core creates a tremendous outward pressure, pushing against the inward crush of its own gravity. For millions of years, these two forces are locked in a delicate balance. But all stars eventually run out of fuel. When our massive star exhausts its nuclear furnace, the outward pressure vanishes. Gravity, patient and relentless, wins the war. In a flash, the star's core collapses. The outer layers are blasted away in a spectacular supernova, but the core keeps crushing itself down into a volume smaller than an atom. The laws of physics as we know them, the elegant equations of general relativity, predict this collapse continues until the core becomes a point of zero volume and infinite density, a singularity. This is a point where our understanding breaks down, where the fabric of spacetime seems to be torn. Surrounding this singularity is the black hole's most iconic feature, the event horizon. It's not a physical surface you could touch. It is the ultimate point of no return. Once you cross this invisible line, the gravitational pull is so immense that the speed required to escape is greater than the speed of light. And since nothing can travel faster than light, escape is impossible. You're trapped. Everything is trapped. Light, matter, information, it all flows one way, inward. To an outside observer, a black hole is defined by what it takes. It's a gravitational vortex, silently consuming whatever strays too close. We can't see the black hole itself, only the chaos it creates. We see stars orbiting a point of pure blackness. We see light from distant galaxies bent and distorted into eerie arcs and rings, a phenomenon called gravitational lensing. Most dramatically, we see the death spiral of matter in an accretion disk. As gas and dust are pulled toward the event horizon, they accelerate to near light speeds, heating up to millions of degrees and glowing brilliantly in X-rays before they take the final plunge. It's a final, luminous scream before an eternity of silence. This one-way nature of black holes is what makes them so unsettling. They appear to be cosmic sinks, information shredders. This has led to one of the most profound puzzles in modern physics, the black hole information paradox. Quantum mechanics, a pillar of modern physics, insists that information can never be destroyed. General relativity, the other pillar, tells us that once something crosses the event horizon, its information is lost forever. This contradiction tells us that there's a crucial piece of the puzzle missing, that our understanding of gravity and the quantum world is incomplete. Then there's the problem of the singularity itself. Nature hates infinities. An infinitely dense point is a sign that our equations have broken down. Physicists have long suspected that a new theory, a theory of quantum gravity, is needed to resolve this paradox and explain what truly happens at the heart of a black hole. This is the black hole, a silent gravitational tyrant, defined by its event horizon and hiding a singularity that defies our laws of physics. It is the ultimate endpoint. But what if it's not? What if the same math that gave us this perfect prison also gave us a perfect escape route? This is where our story takes a dramatic turn. The hypothetical anti-hero, the birth of the white hole. The idea of a white hole didn't come from a science fiction novel. It was born from the same place as the black hole, Albert Einstein's equations of general relativity. Back in the 1930s, long before we had any proof of black holes, physicists like Robert Oppenheimer were exploring these revolutionary equations. They found that the math describing the gravitational collapse of a star had a peculiar symmetry. It didn't care about the direction of time. This is a concept known as time reversal symmetry. Imagine filming a ball falling to the ground. If you run the video backwards, you see the ball fly up from the ground. Einstein's equations showed that if you could run the movie of a black hole forming backwards, the math worked just as perfectly. But what you'd see would be something utterly alien. Instead of a star collapsing, you would see an event horizon spewing matter and energy outward. This time-reversed black hole is, by definition, a white hole. Where a black hole's event horizon is a point of no return, a white hole's is a boundary of no admission. Nothing from the outside universe can ever cross it. Instead, anything already inside a white hole must leave. It's a region of spacetime that can only eject matter and energy. For decades, this was treated as a mathematical curiosity. Physicists argued that while the equations allowed for white holes, nature would have no way to form one. The process of a star collapsing into a black hole aligns with a fundamental law of the universe, the second law of thermodynamics, which states that disorder always tends to increase. A star collapsing into a chaotic singularity is a perfect example of this. But a white hole exploding into existence would be like watching an egg unscramble itself, a massive decrease in disorder, which seemed to violate this ironclad law. So, the case file was closed. White holes were relegated to the dusty shelves of theoretical physics. But the story didn't end there. The very problems that plagued black holes, the information paradox and the singularity, are what brought white holes back. A new generation of physicists began to ask, what if the singularity isn't an endpoint? What if quantum mechanics intervenes? This is the domain of loop quantum gravity, LQG, a leading candidate for a theory of quantum gravity. LQG proposes that spacetime itself isn't smooth but is made of discrete atoms of space and time. According to this theory, you can't just keep crushing matter into an infinitely small point. There's a limit. In this picture, when a star collapses, the matter doesn't form an infinite singularity. It compresses into an unimaginably dense but finite state, something called a Planck star. At this point, the quantum properties of spacetime itself generate a powerful repulsive force, a quantum pressure. This pressure halts the collapse and causes the matter to rebound in a quantum bounce. The collapsing black hole, in a quantum leap, could transform into an exploding white hole. This theory suddenly gives the white hole an origin story. It's not something that had to be there since the beginning of time. It could be the end stage of a black hole's life. This idea could solve multiple problems at once. The singularity is avoided, replaced by a finite quantum bounce. And the information paradox might be resolved. The information that fell into the black hole isn't destroyed. It's stored during the quantum transition and then released back into the universe through the white hole explosion. The cosmic prison now has an escape hatch. This theory transforms the white hole from a thermodynamic impossibility into a quantum possibility. And if black holes can turn into white holes, then the universe might be littered with evidence of their violent rebirths. We just need to know what to look for. The cosmic crime scene, GRBO 60614. Every good detective story needs a crime scene, a piece of evidence that doesn't fit the official story. In our hunt for the white hole, that crime scene is located 1.6 billion light-years away. The evidence is a single, baffling flash of light detected on June 14, 2006. Its name is GRBO 60614. GRB stands for gamma-ray burst. These are the most energetic explosions known in the universe, second only to the Big Bang. For decades, astronomers had sorted them into two neat categories. The first are long-duration bursts, lasting from 2 seconds to several minutes. These are the death screams of massive stars collapsing to form black holes, and they are almost always followed by a bright supernova explosion. The second are short-duration bursts, lasting less than 2 seconds. These are thought to be caused by the collision of two dense objects, like two neutron stars. For a long time, every GRB fit into one of these two boxes. And then came GRBO 60614. Detected by NASA's Swift satellite, this burst was a complete anomaly. On one hand, it was a long-duration burst, lasting a full 102 seconds. This meant it should have been from a collapsing star, and we should have seen a supernova. But astronomers looked, and they kept looking, and there was nothing. No supernova. This was a death scream with no dying star. The lead author of the paper in Nature that first described it admitted, "This is brand new territory. We have no theories to guide us." The file for GRBO 60614 was an unsolved case. And into this vacuum stepped a bold new suspect. In 2011, astronomers Alon Retter and Shlomo Heller published a paper with a radical suggestion. What if GRBO 60614 wasn't a black hole being born, but a white hole erupting? They argued that the emergence of a white hole would be a spontaneous, violent event, a small bang, that ejects all its matter in a single, powerful pulse. You wouldn't see it continuously. You'd only detect the explosive event itself before it fades. This perfectly matched the profile of a gamma-ray burst without a supernova. The burst was the event. This hypothesis electrified the field. Here was a real-world observation that could potentially be the first evidence of a white hole. It transformed the white hole from a purely theoretical concept into a testable idea. Of course, this is not the only explanation. Other theories, like a new type of merger event, have also been proposed, and there is no scientific consensus that this burst was definitively a white hole. But that single, baffling event pried the door open. It showed that there are still profound mysteries in the high-energy universe that our models can't explain. It provided a tantalizing piece of circumstantial evidence. The crime scene is there. The evidence is on the table. Now, we need to understand the weapon. We're about to explore the physics of what this cosmic volcano would actually look like. This is where science pushes the boundaries of imagination. If you're enjoying this journey into the cosmic unknown, take a moment to subscribe. We explore questions like this every week, and you won't want to miss what's next. Now, let's get back to the investigation. The investigation, visualizing a cosmic volcano. We have a motive, resolving deep physics paradoxes. We have a suspect, the white hole. And we have a potential crime scene, GRBO 60614. Now, let's go deeper. What would one of these things actually look like? Let's begin from a safe distance. Imagine you're watching a patch of empty space. Suddenly, a point of light appears in an instantaneous flash. This is the small bang, the moment the quantum bounce occurs and the white hole bursts into existence. Unlike a black hole that lurks in shadow, a white hole would be a beacon of ferocious light. Its core would blaze with impossible intensity, a searing point from which matter and energy are ejected at near light speeds. You'd see a torrent of superheated plasma, fundamental particles, and raw energy expanding outwards in a radiant, spherical shell. The event horizon itself would shimmer and distort the view behind it. The extreme gravity, even as it pushes outward, would still warp spacetime, creating a powerful gravitational lensing effect. Starlight from distant galaxies would be bent into haunting rings and arcs, creating a cosmic halo around the erupting core. The colors would be dazzling, intense blues and brilliant whites close to the event horizon, fading into fiery oranges and deep reds as the ejected material expands and cools. Now, for the signature our telescopes would detect. The leading theory is that the black-to-white hole transition would convert the mass of the collapsed star into an immense flash of high-energy photons. A gamma-ray burst. Just like GRBO 60614. But the show might not end there. Some theories suggest a connection to Hawking radiation. Stephen Hawking predicted that black holes slowly evaporate by emitting faint radiation. Since a white hole is a time-reversed black hole, its explosive gush of matter and energy could be seen as a time-reversed form of this evaporation, not a slow leak, but a torrential downpour. Other, more exotic ideas have been floated. For a while, some physicists, including Carlo Rovelli, wondered if some of the mysterious fast radio bursts, short, powerful blips of radio waves, could be the dying cries of tiny, primordial black holes turning into white holes. While a connection to white holes now seems less likely, as most FRBs are attributed to other sources like magnetars, it shows the kind of unique signatures physicists are looking for. Now for the true heart of the violence, the quantum bounce itself. This is where loop quantum gravity provides the engine for our cosmic volcano. As matter inside a black hole reaches the maximum density allowed by quantum gravity, spacetime itself pushes back. This isn't a normal explosion. This is the fabric of reality rebelling against infinite compression. The result is a rebound so violent it would send ripples through spacetime itself, gravitational waves. Detecting these specific gravitational wave signatures could one day be the smoking gun evidence for this transition. The scale of this violence is hard to grasp. According to calculations by physicists Hal Haggard and Carlo Rovelli, even a tiny black hole would detonate with incredible force, releasing all the information it had ever swallowed in a single, brilliant flash. On larger scales, the ejected material, rich in elements forged in the original star and processed through the quantum bounce, could become the seed material for new stars and planets. A white hole isn't just a destructive force. It's a cosmic recycler, violently rebirthing dead stars as the building blocks for new worlds. The grand revelation: are we living inside a white hole? We've been hunting for white holes as individual, distant objects. But what if we've been looking in the wrong place? What if the biggest clue has been all around us all along? This is the most mind-bending idea in our investigation: the theory that the Big Bang itself was a white hole. Let's look at the Big Bang theory. It tells us that 13.8 billion years ago, the entire universe was contained in a point of unimaginable density and temperature, a singularity. From this point, it began to expand and cool. But doesn't that sound familiar? An event where all matter is ejected in a single pulse from a singularity-like state. As some physicists have pointed out, the Big Bang looks, geometrically and behaviorally, almost identical to the description of a white hole explosion. This isn't just a superficial resemblance. The idea is rooted in attempts to understand what came before the Big Bang. The Big Bang singularity, like the black hole singularity, is a point where our physics breaks down. The theory of a big bounce, which arises naturally from loop quantum gravity, offers a compelling alternative. In this scenario, our universe is part of an eternal cycle. A previous universe collapsed under its own gravity in a big crunch, but instead of ending in a singularity, it underwent a quantum bounce. The collapsing universe rebounded and emerged as our expanding universe. In this picture, the Big Bang wasn't a beginning, it was the moment of the bounce. And the event that propelled all that matter and energy into our new cosmos was, by definition, a supermassive white hole. We are, in effect, living in the expanding debris field of the ultimate cosmic volcano. Our universe is the white hole. This idea, known as white hole cosmology, elegantly solves the problem of a beginning from nothing. It also offers a stunning connection between the largest and smallest scales. Every black hole in a parent universe could become a seed for a new one. This theory has gained traction because it makes predictions. Some cosmologists are searching for signatures of this big bounce in the cosmic microwave background, the faint afterglow of the Big Bang. Such evidence could confirm that our universe was born from the ashes of a previous one. The implications are almost too vast to grasp. It would mean that black holes are not just cosmic graveyards. They are wombs, engines of cosmic renewal. This model also provides a new lens through which to view other mysteries. Some speculative ideas suggest that these bouncing primordial black holes could be a source of dark matter. In a 2014 paper, Carlo Rovelli and Francesca Vidotto proposed that microscopic white holes, the stable remnants of evaporated primordial black holes, could be scattered throughout the universe, their collective gravity accounting for the missing mass we attribute to dark matter. Dark matter might not be some exotic, unknown particle, but the ghostly remnants of countless, small bangs. This grand revelation ties all the threads of our investigation together. The lonely gamma-ray burst, the quantum bounce, dark matter, and the Big Bang itself might all be different facets of the same underlying story. The story of the white hole. We may not just be hunting for a violent object in the sky. We may be living inside of one. An open case file. Our investigation has taken us from the darkness of a black hole to the theoretical fires of a white hole, and finally, to the very beginning of our own existence. We started with a premise that the opposite of a black hole would be an object of unimaginable violence. We found that this violence might not just be destructive, but creative, a force that could resolve deep paradoxes, recycle information, and even birth universes. So, is the case closed? Not at all. We have no definitive, smoking gun evidence of a white hole. GRBO 60614 remains an intriguing but unconfirmed suspect. The idea that the Big Bang was a white hole is a powerful theory, but it remains on the frontiers of cosmology, awaiting crucial data. The theory that dark matter is made of tiny white holes is just one of many competing hypotheses. White holes remain, for now, in the realm of the hypothetical. They exist in the fascinating gray area where mathematics and observation have yet to fully align. Their very nature might make them ephemeral. A white hole could flash once and then be gone, its effects fading into the background. But this is how science works. It's a process of chasing ghosts and pushing theories to their limits. The story of the white hole began as a mathematical oddity, was dismissed as an impossibility, and has now been resurrected by quantum mechanics as a potential key to unlocking the universe. Whether they are exploding in distant galaxies, making up the dark matter that holds our own galaxy together, or whether we are living in the grandest one of all, the idea of the white hole has fundamentally changed our understanding of the cosmos. It tells us that endings may not be final. It suggests that from total collapse, a new and violent beginning is possible. The universe may not be a one-way street to oblivion, but an eternal, pulsating cycle of collapse and rebirth. The case file on the white hole remains wide open. The hunt continues, and it challenges our deepest assumptions about space, time, and creation itself. So, I'll leave you with a final question. If every black hole is a potential doorway to a new beginning, what kind of universe will ours one day create? What do you think? Is the Big Bang the ultimate white hole? Is dark matter made of the remnants of tiny, bouncing black holes? Let me know your theories in the comments below. These conversations are where exciting ideas are born. And if you enjoyed this journey to the edge of science, please consider liking this video and subscribing for more. Your support allows us to keep asking these big questions. Science just discovered what black holes actually lead to. Ever since we first gave them a name, black holes have been the ultimate symbol of cosmic destruction. A one-way ticket to nowhere. A place where the laws of physics get crushed out of existence, and where matter, space, and even time itself, just end. We've always been told a black hole is the universe's final punctuation mark. A full stop. But what if that's not the whole story? What if the greatest endings are also the most violent beginnings? What if everything we thought we knew about these cosmic graveyards was wrong? What if, instead of being a tomb, a black hole is actually a womb? This isn't science fiction. This is the story of a revolution stirring in cosmology, a radical new idea that suggests the death of everything inside a black hole is actually the chaotic, beautiful, and fiery birth of an entirely new universe. So prepare yourself, because we are about to journey past the point of no return to ask, what truly lies on the other side? The answer might not just change how we see the universe, it might change our understanding of existence itself. The perfect prison, our classic picture of a black hole. To understand the revolution, you first have to understand the old rules. We have to build the prison before we can talk about the escape. And in the entire cosmos, there's no prison more perfect than a black hole. Our story starts, as so many cosmic tales do, with death. Imagine a star, way more massive than our sun. For millions of years, it's a glorious furnace, fighting against the crushing force of its own gravity with the outward push of nuclear fusion. But the star is getting old. Its fuel is running low. And then, the fire goes out. In an instant, gravity, the silent, patient force of the cosmos, finally wins. The star's outer layers explode in a supernova, one of the brightest light shows in the universe. But the core, the star's heart, has a much darker fate. It collapses in on itself, catastrophically. The more it collapses, the stronger its gravity gets. The stronger its gravity gets, the more it collapses. It's a runaway train of unimaginable violence. Matter gets squeezed into a smaller and smaller space, until its gravitational pull becomes so powerful it wraps spacetime around itself like a shroud. This is the birth of a black hole. And at its edge, a line is drawn in the cosmic sand, the event horizon. This isn't a physical wall you could bump into. It's way more profound. It is the point of no return. Once you cross it, the direction we call forward in time, and the direction toward the black hole's center become the same thing. To move forward is to fall deeper in. There's no escape. Not for you, not for a planet, and not even for a beam of light. All paths lead inward. This picture comes straight from Albert Einstein's theory of general relativity. It describes gravity not as a force, but as a curve in spacetime. Think of spacetime as a stretched rubber sheet. The sun is like a bowling ball making a gentle dip that planets roll around. A black hole, though, is like dropping a tiny, impossibly heavy ball bearing onto that sheet. It doesn't just make a dip, it punctures it, creating a well that goes down forever. This is the classic, terrifying, and awe-inspiring picture of a black hole. So, what happens if you take the fall? If you cross the event horizon? According to general relativity, it's not pretty. The tidal forces, the difference in gravity between your head and your feet, would stretch you into a thin stream of atoms, a process gruesomely nicknamed spaghettification. As you fall, time would get weird. To someone far away, you'd seem to slow down and freeze at the edge of the horizon forever. But from your point of view, the universe outside would speed up, and you'd watch eons of cosmic history flash before your eyes in an instant. And where does it all end? At the heart of the mystery, the central flaw in the story, the singularity. General relativity predicts that all the matter that ever fell in gets crushed into a single point with zero volume and infinite density. A place where all the known laws of physics, the very rules of reality, break down. Space and time stop having any meaning. It is, quite literally, the end. For almost a century, that's where the story stopped. We've even seen these monsters. The Event Horizon Telescope gave us our first direct picture of the shadow of M87*, and later, Sagittarius A*, the beast in our own Milky Way. They're real. Their prisons are real. But physicists have always had a deep, nagging suspicion about that final destination. Because in physics, the word infinity isn't an answer. It's a sign that your theory is broken. Nature doesn't do infinities. It's a clue, the first major clue in our detective story that something profound is missing from the picture. The ghost in the machine, the information paradox. Every good detective story has a moment where a new piece of evidence turns the whole case upside down. In the story of black holes, that twist came not from the world of the very big, Einstein's gravity, but from the bizarre world of the very small, quantum mechanics. This is the other pillar of modern physics. If general relativity is the grand stage, quantum mechanics describes the actors, the particles and forces that make up reality. And for 100 years, these two theories have been in a cold war. At the heart of their conflict is one simple, unbreakable quantum rule: information can never be destroyed. Now, when physicists say information, they mean the fundamental quantum properties of every particle, its position, its spin, all the things that make it unique. You can scramble this information, you can burn a book and scatter the ash, but the original information is never truly lost. It's always preserved, encoded in the smoke, the ash, and the heat. For a while, this wasn't a problem. Black holes were eternal prisons. Information went in, and it stayed in. Problem solved. Then, in 1974, Stephen Hawking made a discovery that shook physics to its core. He showed that black holes aren't completely black. They glow with a faint thermal energy, now called Hawking radiation. Over unimaginable timescales, this glow causes the black hole to slowly lose mass, to shrink, and eventually, to evaporate completely in a final flash of light. And suddenly, physics had a huge crisis on its hands. The black hole information paradox. Here's the problem. You throw a book, full of information, into a black hole. The black hole slowly evaporates over trillions of years, leaving behind nothing but a random, featureless gas of Hawking radiation. So where did the information that made up the book go? It can't be in the black hole is gone. And according to Hawking's original math, it's not in the radiation either, because the radiation is random. It looks like the information has been completely erased from the universe. This is a catastrophe. It means either general relativity is wrong, or quantum mechanics, the most successful scientific theory in history, is wrong. You can't have both. For decades, physicists have been desperate to solve this puzzle. The search has led to some wild ideas. The prevailing view today is that Hawking's first calculation was incomplete. Many physicists now believe the information does escape, scrambled up in the outgoing radiation. Ideas like the holographic principle suggest that information isn't stored inside the black hole, but on its two-dimensional surface, the event horizon, ready to be imprinted back onto the radiation. These are powerful, elegant solutions. But they aren't the only solution. A more radical, more explosive idea has been lurking in the shadows. What if the information doesn't leak out? What if the black hole doesn't just evaporate into nothing? What if it transforms into something else entirely? To find this suspect, we have to look for a ghost that has haunted the equations of relativity from the very beginning. The fugitive. Introducing the white hole. In physics, there's a deep and beautiful symmetry. For every particle, an antiparticle. For every action, an equal and opposite reaction. And in Einstein's mathematics, the black hole also has a twin. A perfect, time-reversed mirror image. It's called a white hole. If a black hole is the ultimate trap, a white hole is the ultimate fountain. It's a region of spacetime that nothing can enter from the outside. A black hole's event horizon only lets things in. A white hole's event horizon only lets things out. It's an explosive expulsion of matter and energy. The idea of a white hole isn't some new, weird invention. It comes from the exact same equations that predict black holes. Mathematically, they are just as valid. So why have we all heard of black holes, but white holes are basically unknown? Because for all their mathematical beauty, there was a fatal flaw. You couldn't make one. To form a black hole, just collapse a massive star. Gravity does the work for you. But how would you form a white hole? Since nothing can get in, it can't be formed by the collapse of anything. It would have to have just been there since the beginning of time. It seemed like a mathematical fantasy, a ghost in the machine that physicists mostly dismissed. For decades, the white hole was a fugitive from reality. We had a culprit, the black hole, and a crime, the information paradox. But this new suspect had an unbreakable alibi. It couldn't exist because there was no way for it to be born. But what if the alibi is flawed? What if a white hole isn't something that forms on its own? What if it's the asterisk end of a black hole? This is where our story takes a sharp turn. A new generation of physicists are starting to believe they aren't two separate things. They are two acts in the same cosmic play. A transformation. We're at a cosmic crossroads. On one side, the black hole, a place science tells us is an ending. On the other, the white hole, a theoretical impossibility. The official story says they never meet. But a bold new theory suggests the prison doesn't just hold its captives forever. It transforms them, and itself, into the fountain. If you're finding this cosmic detective story as mind-bending as we are, make sure you subscribe and ring that notification bell. Because the next clue doesn't just connect these two mysteries, it could rewrite the entire story of our universe. A quantum bounce? The case had gone cold. We had a singularity where physics breaks and a paradox that pits our two best theories against each other. To break the case wide open, we need to go beyond Einstein and into the quantum world of gravity itself. The singularity and the information paradox are both symptoms of the same problem. They happen where gravity is super strong and space is super small. This is where general relativity and quantum mechanics fight. To fix this, we need a theory of quantum gravity. We don't have a perfect one yet, but we have some promising candidates. And one of them, called loop quantum gravity, LQG, offers a stunning new possibility in our mystery. LQG says something radical. The fabric of spacetime isn't a smooth, continuous sheet. It's quantized. It's made of fundamental, indivisible chunks, like a digital image made of pixels. You can't zoom in forever. Space itself has a resolution limit. This one simple idea, that spacetime is grainy, changes everything for a black hole. Let's follow a collapsing star again, but this time, using the LQG rulebook. The star collapses, matter is crushed, density skyrockets. In Einstein's theory, this goes on forever until you hit the infinity of the singularity. But in LQG, that can't happen. You can't squeeze matter into a point of zero volume if spacetime itself is made of unbreakable pixels. You can only squeeze it down until it hits the maximum possible density. So what happens then? What happens when you try to compress something that can't be compressed any further? It bounces. This is the heart of the idea, the big bounce. According to LQG theorists, the singularity never forms. Instead, the collapsing matter hits a state of incredible, but finite density. At this point, quantum gravity creates a massive repulsive force that halts the collapse and violently reverses it. The implosion becomes an explosion. And what is an object that has catastrophically exploded from a point of maximum density, from which matter can only fly outwards? It's a white hole. Suddenly, the ghost has an origin story. In this theory, the white hole isn't a phantom anymore. It's the inevitable endpoint of a black hole's life. The collapse is just Act 1. The bounce is the intermission. The explosion as a white hole is Act 2. It solves the singularity problem by saying the singularity never happens. And it offers a breathtakingly simple solution to the information paradox. The information from the book we threw in isn't destroyed. It's stored during the collapse, processed through the ultra-dense bounce, and then violently ejected in the white hole explosion. Information in, bounce, information out. The quantum law is preserved. Now, there's a crucial twist with time. Due to the extreme time dilation inside a black hole, this whole process, collapse to bounce to explosion, is super fast for the matter itself. But for us, watching from far away, time slows to a crawl. The transition could take billions or even trillions of years. This means the black holes we see today could be incredibly slow motion transformations, patiently waiting for their moment to bounce. And it's not just LQG. Other theoretical paths are also trying to find ways around the singularity, hinting that a transition of some kind might be the answer. Two different paths, two different sets of assumptions, both pointing to the same incredible destination. The black hole doesn't die. It is reborn. The grand reveal, a universe of universes. So let's review the case. We started with the black hole, accused of destroying information and breaking physics at a singularity. The mainstream theory suggests the information leaks out. But we've just uncovered a radical alternative, the bounce. Supported by speculative frameworks like loop quantum gravity, it claims the singularity never forms and the black hole transforms into a white hole, spitting all the information back out. It's a clean, powerful story. But this is where the story goes from a cosmic mystery to a mind-altering revelation. If a black hole in our universe collapses, bounces, and explodes as a white hole, where does it explode? Think about it. A white hole is a violent eruption. If it exploded back into our own universe, we'd expect to see some evidence. The sky isn't filled with random cosmic fountains. This led physicists like Lee Smolin to propose a staggering hypothesis. The white hole doesn't explode back into our universe. The bounce is so energetic it creates a new, fresh, expanding region of space and time. It creates a new universe. Let that sink in. Every black hole could be a seed for a baby universe. When a star collapses here, the bounce on the other side might be the Big Bang for a whole new cosmos. Our universe becomes apparent. This idea is known as cosmological natural selection. It applies evolution not to life, but to the cosmos itself. The theory goes that each time a new universe is born, the fundamental constants of physics might change by a tiny amount. Universes whose laws happen to be good at making black holes will have more children. Universes that can't make black holes will have no offspring. Over countless generations of universes, the ones with laws, fine-tuned for making lots of black holes, will become the most common. This provides a stunningly beautiful explanation for why our universe seems so perfectly balanced for life. The laws of physics seem tailor-made for us. Tweak any of a dozen constants, and stars wouldn't form, chemistry would be impossible, and life as we know it couldn't exist. Why is our universe so special? This theory answers. It's not special, it's asterisk fit. The same conditions that allow for stable stars and complex chemistry, the things you need for life, also happen to be great for making black holes. We find ourselves in a universe that can support us because the universes that asterisk couldn't simply didn't reproduce. And this leads to the final, dizzying question. If black holes make new universes, where did our universe come from? The logical conclusion is that our own Big Bang, 13.8 billion years ago, was the white hole explosion from a black hole in a parent universe. Our entire cosmos, every galaxy, every star, every one of us, may have been born from the heart of a black hole in another reality. The search for a smoking gun. This is an extraordinary story. Cosmic death and rebirth, universes creating universes. But science is about testing ideas, not just telling cool stories. A theory, no matter how elegant, is useless unless you can look for evidence. So, where's the smoking gun? It's incredibly difficult, but maybe not impossible. The bounce itself would send shudders through spacetime called gravitational waves. Our detectors on Earth, like LIGO, listen for high-frequency waves from things like colliding black holes. A slow, cosmic bounce, however, might produce very low-frequency waves. Detecting those is the goal of a future space mission, the Laser Interferometer Space Antenna, or LISA, set to launch in the mid-2030s. It's designed to hunt for these exact kinds of low-frequency whispers, and a signal from a bouncing black hole is one of the things it could theoretically find. No such signal has been found, but with LISA, the search is about to begin. What else? Some have speculated that tiny black holes formed in our own Big Bang could have bounced very quickly, and their white hole remnants could still be zipping through the cosmos, possibly even making up some of the mysterious dark matter. This is a very fringe idea, and it's not a leading theory, but it's an intriguing thought. For a while, there was excitement that powerful signals called fast radio bursts, FRBs, could be the final gasp of evaporating primordial black holes. But as we've gathered more data, the evidence now points overwhelmingly to a type of neutron star called a magnetar. So, the search continues. We have a compelling theory, but we're still looking for a definitive witness. We haven't found the smoking gun yet, but for the first time, we know what we might be looking for. So, has science really discovered what black holes lead to? The honest answer is complex. We haven't closed the case. There is no definitive, observational proof of a cosmic bounce. The title of this video is a provocation. It reflects a profound shift in thinking, not a confirmed fact. What science has discovered is a credible, compelling, and mathematically sound path away from the dead end of the singularity. We've discovered a way for the story to continue, a way for both quantum mechanics and general relativity to be right. Speculative theories like loop quantum gravity have opened a door that was locked for a century, giving us a plausible story where the black hole isn't a tomb, but a chrysalis. The image of the universe has changed. It might not be a story with one beginning and a slow, cold end. It could be an eternal ecosystem, a cosmic garden where universes bloom from the seeds of black holes, each one giving rise to the next in an infinite, majestic cycle. The black hole has been transformed from a symbol of destruction into a cosmic phoenix, a promise that every ending might just be a new beginning. We don't have the final verdict. The jury is still out. But the questions we can now ask are grander than ever. If our universe was born from a black hole, what kind of universe was its parent? And what new, unimaginable universes will the black holes in our own cosmos one day create? The mystery, as always, continues. What do you think lies on the other side? Is it oblivion, or the spark of a new Big Bang? Let us know your thoughts in the comments below. And if you enjoy exploring these grand cosmic questions, make sure you're subscribed and have notifications turned on. Thanks for watching.